So, should I start? I can just show you myself a little bit and then,
Yes, sure.
so that is to show that I am here. Okay.
Yes.
So, because of connectivity, I'll just switch off the video and begin the talk. Okay. So, thank you for inviting me, and thanks to Sunandan, Amitabho, and everyone in the Esenbos Center. So it would have been nice if I could have been there, but that's not the case. So this talk is about wormhole spacetimes, as you can see, and I'll come to the result which is mentioned here towards the end. But I will try to give a general introduction at the beginning, spend some time on that general introduction, and then after that I will move on to discussing the specific result which is mentioned here. Okay, so the first slide, as you can see, is about wormholes, what and why. So that's basically giving you a definition and then telling you a little bit about the consequences. So the definition is as follows. Wormholes are essentially the Lorenzian wormholes, as we call them, are non-singular, horizonless, static, spherically symmetric, usually asymptotically flat line elements in a theory of gravitation. So that's the way we will define it. So it could be asymptotically flat, it may not be asymptotically flat also. There are examples of wormholes which are not asymptotically flat. But in general, it is more or less sort of assumed that they are asymptotically flat. They are non-singular, there's no horizon. They are static and spherically symmetric, although there are examples of wormholes which are not necessarily static or even not necessarily spherically symmetric. Now, one of the consequences of such a spacetime, and we will define more mathematically these spacetimes later on, the consequences in words is the following: that general relativity and the assumption of matter satisfying energy conditions, that's the theory general relativity and the fact that matter satisfies energy conditions together, they rule out wormholes. Okay. On the other hand, if we allow violations of the energy conditions, they may exist, but then that needs to be justified. So this is basically, these are the two, this is the definition, and then this is essentially a consequence which has been worked out, and I'll show it also as we go along. So then why are we studying them? So that's an obvious question. If it's ruled out in general relativity, then why are we studying them? But then mind you, I have said here in this, I have said theory of gravitation. So there are modified theories of gravity where these can happily exist. Now, as space-times, the reason why we study them is that they are good in every sense. Now, what do I mean by good? So when I say good, I would basically mean the singularity is a problem in general relativity. So non-singular is something good. Horizonless, whether it's good or not is debatable, but then it's less problematic to some of us. And if it's asymptotically flat, well and good. If it's not asymptotically flat, then also it's fine. So when I say good, I basically mean the fact that they are non-singular. And they may be there in modified theories. And why are they there in modified theories? We want to circumvent this problem. Okay. So they are there in modified theory simply because of an advantage. And what is that advantage? That advantage is the geometry of the wormhole implies a violation of what are called the convergence conditions in Lorenzian geometry. Okay. So a convergence condition is basically like Rij ui uj greater than equal to 0. So their geometry implies a violation of the convergence condition, now which for general relativity directly implies a violation of the matter energy conditions, because you can relate the Ricci tensor with the energy momentum tensor, a combination. And the important word here is that this is a direct relationship. So if you say that the convergence conditions are violated, then the energy conditions are also violated. But this relation between the convergence conditions and the energy conditions is not direct and is different in modified theories. And that's why you say that the matter can satisfy the energy conditions, but still the convergence conditions can be violated. So you have the geometry, you have good matter which satisfies the energy conditions, and therefore you are happy, you can have wormholes. That's not the case in general relativity. Okay, so therefore that's the what of this kind of spacetimes. Now why, of course, is related to whether there is some new physics involved. For instance, if they are observed, that will imply a host of new physics ideas. Now what are those new physics ideas? So one of them is negative energy density in the context of general relativity, or viability of a modified theory of gravity, or extra dimensions, or at least a new geometry. So these are kind of four things that you can have or can think in terms of new physics ideas if there are wormholes. Now, there are other exotic things which people have tried out. Exotic and perhaps unphysical consequences of general relativity, like time machine models or closed time-like curves, can become possibilities if wormholes are found. So that's another kind of, like it or not, that's another kind of new physics idea. And finally, gravitational wave astronomy, as well as other astrophysical observations like imaging, lensing, etc. These could be tools for detection and verification whether these geometries are there or not. And deriving possible detectable signatures is, of course, a viable research program. So you can see that there are three things. You have a host of new physics ideas which are there, which can be studied if we like wormholes. Well, you can have very exotic things also. You can study them and see whether they are meaningful or not. It has been studied to a great extent. And there's, of course, the observational aspect, which you can look into and look for detectable signatures. And that's something which is also going on. Okay, so that gives you the motivation that why do you want to study wormholes, what the wormholes are, and why do you want to study them. So these are spacetimes which were named by John Wheeler in the late 50s, and we'll come to that, what Wheeler did. So let me go back to a little bit of history, although all of you know this, but still let me repeat it. Because the wormholes themselves have a long history as such. So November 18, 1915, we know that general relativity is announced, and Einstein logically completes the understanding and extension of the relativity principle and develops his general relativity. Then in January 13, 1916, Schwarzschild submits an article on the first exact solution in GR. And in February 24, 1916, barely a month later, he submits another paper on the interior solution, which all of us know. And then Schwarzschild passes away at 42, May 11, 1916. After that, the same year, September 3, 1916, Ludwig Flam submits a paper called Contributions to Einstein's Theory of Gravitation. And among other topics, Flam discusses the geometry of Schwarzschild spacetime for the first time here. And you can find a translation of Flam's original paper in the June 2015 issue of General Relativity and Gravitation, the foreword by Gary Gibbons and a biography of Flam. So why I'm talking about Flam? Because of this paper. And all of you have studied what is known as Flam's paraboloid in your elementary general relativity course. So let me just refresh your memories on that. Schwarzschild spacetime is given by this. If you take a 2D section, you get this. T equal to constant, theta equal to pi by 2. You take a background coordinate and line element, cylindrical coordinates. You choose a profile function in this, and you get a 2D metric for z equal to zr. You compare with this 2D section, this one, and then you integrate dz dr to get z square r equal to this. So that's a paraboloid. And rotating this curve about the z-axis gives a paraboloid. So that's the surface of revolution. This is the geometry of the Schwarzschild solution as such, the 2D section. And this is Flam's paraboloid. Now, Flam did not notice the two-sheeted property of the 2D section, which I'll come to in a moment. So he drew a picture with some, in the paper you will find a picture which looks like this. Okay, so it's like a half of what really it should be. Okay, and this is Flam's famous paraboloid. So after 1916, almost 20 years later, in 1935, Einstein wrote two papers. Now, the first of these papers was Einstein, Podolsky, and Rosen, and it's called Can Quantum Mechanical Description of a Physical Reality Be Considered Complete? And this led to the EPR paradox, which all of you know. And the other paper is by Einstein and Rosen again. Okay, not Podolsky. The particle problem in the general theory of relativity. So this paper actually led to the birth of the idea of wormholes. So this is the first precursor. Apart from Flam, this is the first precursor of what is known as wormholes today. Now, these papers keep coming back. For instance, in 2013, a link between the ideas in these two seemingly different kinds of papers was found under the heading of ER equal to EPR. And this is something which is conjectured by Susskind, Maldacena, and Van Ramstonk, which says very briefly that a non-traversable wormhole, Einstein-Rosen bridge, is equivalent to a pair of maximally entangled black holes, which is the EPR pair. And that's the meaning of the statement ER equal to EPR. Okay, so let's discuss. So we will now switch over to this, what was there in this paper as such, Einstein-Rosen. We are not interested in ER equal to EPR or the EPR paradox. So what's the Einstein-Rosen bridge? So what does Einstein think at that time? Einstein worried about how to incorporate particles in the framework of general relativity, which is a classical field theory. So he was aware that there is this kind of singularity at r equal to 2m, which later on we knew or we know today that it's a coordinate singularity in Schwarzschild, and he did not like it. So, but people didn't understand. So Einstein and Rosen rewrote the Schwarzschild line element using a new coordinate. And this is what is known as the u coordinate. So this is the u coordinate. U runs from -infinity to infinity. And if you take the Schwarzschild and rewrite it, you will get something like this. Now, what does this coordinate change do? So it discards the region from 0 to 2m. As you can see, it is r minus 2m. So that is discarded because otherwise u square will become imaginary. And twice covers the asymptotically flat region from 2m to infinity. Okay. Now the region near the u equal to 0 is what is the bridge connecting two flat regions, one at infinity and one at minus infinity. So this is the two-sheeted structure. And this was the Einstein-Rosen bridge, which Einstein thought would geometrically represent a particle. So that's a picture. So u is greater than 0 above and u is less than 0 below the throat. U equal to 0 is the horizon. And the metric determinant vanishes at the throat. Non-traversable wormholes. And the bridge is what Einstein called the particle according to his idea. And then there were some generalizations which he worked out, which he said he talked about something called a quasi-charged bridge, which is a mutated Reisner-Nordstrom solution. Why mutated? Because you have a minus sign here as opposed to a plus sign in the usual Reisner-Nordstrom. And this leads to negative energy density as the source. So the mutation was necessary to allow a horizon when m equal to 0. Otherwise, you get a naked singularity. And this by itself, this mutated Reisner-Nordstrom solution is an example. It's the first example of an energy condition violating space-time in the context of general relativity. Okay, so if you take a special case, if you take m equal to 0 and write the line element like this, and you take this as the bridge coordinate, it represents a massless quasi-charged object with negative energy density. You say quasi-charged because, of course, you have a minus sign over here, and that's why he called it quasi-charged. Now, Einstein, strangely enough, thought that this geometry would represent the electron. Now, this is a kind of pretty vague idea, and it's not true also. So the Einstein-Rosen idea of a particle did not survive and is considered wrong today. But the ER bridge idea remains. And the same happened with the EPR paper also. All of you know that both the 1935 papers led to much work and debate later. And so the fact remains that even if Einstein is wrong, there is something right in what he says. And that something leads to a lot of work. Okay, so that was 1935, and then we jump to 1973. Now in 1973, these two people, Kirill Bronikov and Homer Ellis, they proposed a new line element which has the following ultrastatic limit. When I say ultrastatic, I mean G00 equal to -1. So this was the so-called Bronikov-Ellis spacetime. And you can see that the Einstein-Rosen bridge construction required a geometry with a horizon. Otherwise, the new coordinate is not meaningful. The Bronikov-Ellis spacetime is a horizon-free geometry with G00 equal to -1. And it is the m equal to 0 Reisner-Nordstrom solution with G00 equal to -1. So this is a very special spacetime, and we will talk about its speciality in a moment. How is it generated? What's the matter field? So the matter field is pretty absurd. It says that if you take a wrong sign in the sense the kinetic energy term has a minus sign. If you take a wrong sign massless scalar field, which is fashionably called phantom, then that's a source for this Bronikov-Ellis spacetime. Well, you can use what is called tachyon matter. You can use Hoyle-Narlicker C field as sources, which has been shown in various papers. The interesting thing is that the t equal to constant theta equal to pi by 2 section of this spacetime is a zero mean curvature surface, which is called a catenoid. And despite the fact that you have a wrong sign massless scalar field, it's still, you can show that this is a solution. So this is a Lorenzian wormhole solution. In fact, the first example of a Lorenzian wormhole solution. And the matter required, of course, supports geometry, violates the weak energy condition, and there is negative energy density. But still, it is a solution. Okay, so that is 1973, and then we turn back again to John Wheeler, Misner and Wheeler in 1955. So this is the context in which wormholes first appeared in this paper called Classical Physics as Geometry. And here Wheeler and Misner proposed the maxim physics as geometry and introduced the term wormhole. And this is the famous example of charge without charge. So they considered the single sheeted spacetime with a space-like slice, which had a handle. That was the electric field lines that you can see in green over here. And if you are sitting on this surface, you are oblivious of this handle over here, then it would seem to you, to the observer on the flat surface who is oblivious of the handle, the location of the mouths would seem to suggest the presence of a charge because of the diverging and converging electric field lines. And this is what is known today as the topological model of an electric charge. So thus, even though there is actually no charge, one can perceive the presence of positive and negative charges at the mouths, and this is what Wheeler called as charge without charge. So the geometry with a handle is what they called as the wormhole. And nowadays, the two-sheeted Einstein-Rosen bridge and the single-sheet Wheeler wormhole geometry are both termed as wormholes. So you have three pictures over here which I have drawn. The first one is topologically different from the rest, and the third one is used in the time machine construction of Morris Thorne and Yatsever in 1988. So that's the first picture. Two asymptotically flat spaces connected by a bridge, non-singular. This is the handle picture, and this is the kind of picture one uses, the shortcut picture, which helps you in constructing a time machine model, which has been done by Morris Thorne and Yatsever. And that time, the years after that, there was a lot of work on such closed time-like curves and time machine models. There are also Euclidean wormholes, which are solutions of the Euclidean Einstein equations. And the most well-known example is, of course, the Giddings-Strominger Euclidean wormhole of 1988, which led to a lot of work. And the theory in this paper is the matter part of the action is a rank 3 antisymmetric tensor field coupled to gravity. And you find these are instant-on solutions, finite action, representing nucleation of a baby universe, and an example of what is known as topology change. And you can show that this model, this kind of wormholes, represent the instant-on which leads to topology change from R3 to R3 plus S3. And then one can find the nucleation rate. The Euclidean action is finite in this case, and you can use the path integral methods in Euclidean quantum gravity. But Euclidean wormholes have problems, and therefore, why they have problems? Because the Euclidean quantum gravity formulation itself has its own problems, which I shall not discuss. But this is just to tell you that there is another branch of wormhole physics which discusses the Euclidean type of solutions, which are known as Euclidean wormholes, and they are solutions of the Euclidean Einstein equations. Okay, so let me now turn to Lorenzian wormholes. So I have a Lorenzian line element, which is this. I have a psi r and a br. So this is the work of Morris Thorne and Yatsever in 1988. The psi r and br, these two have certain conditions. For instance, this has no zeros. The G00 has no zeros, so therefore no horizons. The B at r equal to B0 is B0. and BR by R is less than equal to 1, otherwise the signature gets affected. So this is called the shape function. And of course, if you impose asymptotic flatness, then you need to have BR by R tending to 0 as R tends to infinity. And if you have a psi R, of course, you need to have the property that psi e to the 2 psi R goes to 1 as R goes to infinity. Now, if the above hold for psi R and BR, then we have a Lorenzian wormhole. Now, there could be further constraints on traversability obtained via geodesic deviation and relative force, which I am not going into. As a space-time, as long as you satisfy these three conditions, you can construct a line element which represents a Lorenzian wormhole. Now, let me give you some examples. If you take your Schwarzschild solution and you make G00 equal to 1, you get what is called the Schwarzschild wormhole. Bronikov-Ellis I have already talked about. You can think of a modified Schwarzschild, which we talked about in our paper many years ago, which is this, which has a zero Ricci scalar also. Then you can, there is something called the Damur-Solodukin solution of 2007, where they did the intelligent thing of making M1 and M2 in the Schwarzschild solution and making sure that M1 is not equal to M2 and M1 is less than M2 and R is greater than equal to 2M2. So that represents a wormhole also. Then more recently, there is the work by Simpson and Visser, where you have a sort of hybrid kind of geometry, where if you put M equal to 0 in this, then you get Bronikov-Ellis. If you put B0 equal to 0, you get Schwarzschild. So these are nice examples of wormhole spacetimes, and there are many more examples of wormhole metrics which exist in the literature. So what about energy conditions, energy condition violations? Now the weak energy condition is given by this expression, and rho is greater than equal to 0, rho plus tau is greater than equal to 0, and rho plus p is greater than equal to 0, where rho is the energy density and tau p are the pressures in a diagonal Tij. And the null energy condition is given by this, without this condition. And there are local and averaged energy conditions which also exist. So now if you take this line element and you work out the Einstein tensor, you could write the energy density and the radial pressure in terms of these expressions. And then if you impose the weak energy condition inequalities, then you need to have this, which tells you that b prime r minus b by r cube has to be greater than or equal to 0 at the throat, because at the throat this term is 0. Now if you take the two-dimensional section and you embed it in a Euclidean background, which is given by this with a certain profile function, so that's a picture. And then you find out what is dz dr by comparing these two. That is, you take z equal to zr over here, you get a two-dimensional metric and write down an equation for dz dr, which is given by this. Turn that around, get dr dz, and then take the second derivative, you get something like this, which means your r of z, if it has to have a minimum, because that's what should happen at the throat, which is at z equal to 0. So for a wormhole throat to exist, d2r dz2 has to be greater than 0. And therefore b minus b prime r is greater than 0. On the other hand, if you recall, what did I get earlier? From this inequality, I can see that at r equal to b0, this term is 0. So therefore b prime r minus b is greater than 0, which means b minus b prime r is less than 0. So that's the contradiction. And this leads to the fact that matter must violate the null energy condition or the weak energy condition in order to have a wormhole. So this is known as the Morris-Thorne theorem. And there are various ways out. Quantum field theory allows the violation of the energy conditions. Epstein-Glaser-Yaffe theorem. You can calculate the expectation value of Tij over appropriate states, and you can get negative energy densities. Casimir effect is an example. As I said right at the beginning, you can use modified gravity to allow the convergence condition to hold with a violation of the energy conditions and vice versa. One can have evolving wormholes which may violate the energy conditions of a finite interval, and one can constrain the amount of violations of energy conditions to small values, which is something that we proposed in 2003. So today, the main emphasis, of course, is about detection. Gravitational waves, lensing, imaging, these are tools. And the main point is that you look for what are called black hole mimickers. And wormhole is one suggestion. So to understand this, you have to study the quasi-normal modes, scalar and gravitational. You have to set up templates for comparison with GW observations. And of course, you can study gravitational lensing. A lot has been done on this. But the central question, of course, still remains, how can we circumvent energy condition violations? So there have been ways, but the question is, that still remains. That question still remains. So let me now turn to the recent result, which I wanted to discuss. And what I do here is to think of constructing a variant of the so-called Bronikov-Ellis spacetime. So what I do is I write down ad hoc a line element which looks like this, and you can see that I have plugged in a factor over here which is alpha squared r squared with a minus sign. So this is not space-time asymptotically flat, only spatially asymptotically flat. And the source is, as has been shown, it's a phantom scalar plus null energy condition satisfying matter, which can be shown explicitly. Now you can derive this minus alpha square r square by imposing the fact that this spacetime admits, if you take a general function over here and you say that this spacetime admits a conformal killing vector, then you would end up getting a G00 given by this. So that's a mathematical fact which was shown by Boehmer, Harco and Lobo in 2007. The main point is this kind of choice actually localizes the violation of the null energy condition around the throat. And the average null energy condition violation can be controlled with these two parameters. One is alpha and one is B0. So how is that? You take the rho plus tau inequality for this metric by constructing the Einstein tensor and you plot it as a function of r. And you can see that the green graph over here is for B0 equal to 0, which is perfectly positive. The yellow graph over here is for Bronikov-Ellis, where G00 is equal to -1, and it's completely negative. Whereas if you have this piece, then you can see there is a region where it is actually negative, but then beyond that it is positive. And you can also show that this inequality, rho plus p greater than equal to 0, is always true. And this is of course true for general BR instead of the BR which we have chosen. So this is the first. Choosing this ad hoc G00, we can actually localize the energy condition violation to a region around the throat. So now if you propose this geometry, you can study various properties. For instance, you can look at geodesics. And what we found was these are exactly solvable. And you could get closed orbits of this kind for different parameter sets. So this is an example of the closed orbits in the polar plane. And there is an extra condition for closeness, which you can find out in the paper. Then there are also open orbits, which are like this, which are bounded between two values, the throat radius and the D0, which is greater than B0. So these are not closed curves. They just go round and round along this region from B0 to D0. Now, all these solutions are in terms of what are called Jacobian elliptic functions. And for null geodesics, you can find simple functions. And this is all discussed in my paper, very recently published. Okay, you try to look at the scalar wave equation in this geometry, and that's also exactly solvable. So you write phi like this, and your capital R function can be integrated, and you get R of R given by this, where P is this P over here is given by this. And if you plot this R of R, say the sine function over here, you get a decaying solution. So this is perfectly exactly solvable without any issues as such. And same is true for the massive scalar field. So it's a function which is decaying with the radial coordinate R. Now let me go back to something else and see whether I can justify that G00 which I chose. So there is something known as the Witten bubble, which is found by looking at the 5-dimensional Schwarzschild solution and doing a double wick rotation of this 5-dimensional Schwarzschild solution. So this is what is called the double wick rotation. If you do that, then you get a geometry which is this. And this is of course a vacuum solution in 5-dimensional Kaluza-Klein theory. It's a time-dependent solution and it's an ever-expanding bubble. And you get this G00, which is this. On top of it, you have a warped extra dimension, in the sense that the extra dimension is dependent on the one of the 4-dimensional coordinates, which is R. Okay. Now, if you take this Witten bubble, you notice that there is an alpha here and there is an alpha here. So all you do, you just make these different. You take alpha here and a rho 1 here. And if you do this, the slight change alpha not equal to rho 1 allows us to put rho 1 equal to 0 and get a static metric. But then this is non-vacuum. And this is also not obtainable in any wick rotation as such. So both the non-static and static versions are generated by matter satisfying the energy condition. So if you find the Einstein tensor, you check the energy condition, this is perfectly fine. But the advantage is now you can put rho 1 equal to 0 and get a static metric. And this static metric is a wormhole with its chi equal to constant section being the 4D variant of BE geometry discussed earlier. Now the R equal to B0 section has a degenerate induced metric and the extra dimension disappears near the throat. So you see that R equal to B0, this piece goes off, and R going to infinity, this piece is basically R square d chi square. So you can generalize this further. So you propose a metric with a G00 here, with a BR here, and you take psi equal to 0 and you solve your 5-dimensional vacuum Einstein equations and you get an exact solution, which is BR equal to this. And in 5 dimensions, that's the metric, which was noticed by Mark Roberts in 2009 in an unpublished preprint. And if you take 6D, for instance, then you get the Bronikov-Ellis with an S3 over here instead of an S2. And you can go on making further generalizations with different BR and with matter satisfying or violating the energy conditions. So you have a vacuum solution, you have a whole lot of vacuum solutions in different dimensions, and you know how to construct them. The extra dimension decays from a finite value at infinity to 0 value at the throat. There's no issue of energy condition violations for vacuum solutions, but we need higher dimensions. So this is still in preparation. Finally, what about the following metric? So there's a R square d xi square, and I have the usual 1 minus BR by R and 1 minus BR by R here. So this is an unwarped extra dimension xi. Now you compare this with this one over here, where there's a warped extra dimension chi. And you can get one from the other, that is this from this or this from this, by a Wick rotation, tau going to I r chi and xi going to I by RT. Give the second from the first, which you can check immediately. It's very straightforward. Both these metrics have the same Ricci scalar and the same Crashman scalar, but they have different Einstein tensors, and therefore they require the required matter stress energy and the status of energy conditions differ. Now the first one is a black hole with a constant extra dimension. The other one is a wormhole with a warped extra dimension. And we can check the matter and show that the wormholes non-vacuum are there. If the energy conditions are violated, the corresponding black hole will satisfy the energy conditions. Now, why does this happen? So you need to study this more and see whether there is anything worth and deep in this. So in future, you can generalize to metrics which are not allostatic. You can generalize to extra dimensions which of the type SD, d greater than 1. In this case, it was just S1. Partial investigation on geodesics has been done, and you can do more investigations on geodesics surely. You can find examples with possible matter sources describable by a Lagrangian density. And you can study perturbations of various types for these geometries, especially the 5D one. So that's the recent result, and let me now end by giving a critique on wormhole research. Now, what is the criticism? Many a time wormholes are tailor-made. All these solutions that I talked about earlier, Damur Solovykin, Simpson-Visser, Schwarzschild wormhole, these are all tailor-made, not always solutions to field equations. And in some sense, this is what was in early days of general relativity. If you look at the oldest books, in Singh's book, for instance, there is something called the G method and something called the T method of solving Einstein's equations. So in the T method, it's the input is Tij, and in the G method, you write down a metric and say that this is the matter. Now one should find more solutions with a given Tij. So that's one thing which we have to. Yeah, I know time is up. Just 1 minute. Yeah. This is the last slide. Please don't worry.
I just wanted to remind you.
Yeah. Okay. Yeah. This is the last slide. Don't worry. So exotic energy condition violating matter, is that acceptable? And examples and counter examples exist. Only observations can decide. Okay. And if we find a wormhole in gravitational wave observations as an end state of collisions between astrophysical objects, then indirect evidence of exotic matter is there. And one may choose to be less cynical and continue research or turn away. So that's the attitude one may take. And finally, let me just mention that wormholes are in some sense against what normal gravity does, because there is a defocusing at the throat. Okay, so normal gravity is about attractive nature. So they defocus trajectories, and the question is that bad? Well, it happens in many other spacetimes also, and you can show that. But one could be more positive and say that general relativity is not just a theory of gravity, it has much more in store. And we often forget that Einstein called it general relativity. He could have called it a theory of gravity, but he preferred this name. And he thought of it as a logical completion of what was the relativity principle of Galileo. So we should move ahead with expectations on more surprises from general relativity. Thank you.
Wonderful talk. So it's time for some very quick questions. So Golam, please go ahead.
Shananda, I have a
Yes.
question. I mean,
Yeah.
if you please go back to a slide where we had this metric with GTT alpha r square.
Yeah. Which one? This one?
No, the one before. Maybe the this one.
Yeah.
So here, if I at a r, such that 1 minus b naught square r square is negative, then I'll have two negative time coordinates, right?
No. R is greater than or equal to B0. That's by definition.
Okay.
So I'm looking at the region where R is greater than or equal to B0.
But I mean, if I want to look at the other region, what happened to the both the times? Like we'll have two time coordinates?
No, R there. If you can write this metric, for instance, in using what is called the proper radial distance, and then the L will run from minus infinity to infinity. So there will be no problem. That is an artifact. That is the artifact.
Okay.
So if you take R is greater than or equal to B0, that corresponds. If you take dr by root 1 minus B0 square by R square and call it dl. So then there is a L coordinate, which is the proper radial distance, and therefore that L coordinate runs over the entire domain from minus infinity to infinity.
Okay. But if I take it analytic continuation away, then in the sense that R, let's run around from 0 to infinity,
then there will be two time coordinates and you don't know how to define the metric as such, because there will be another actually here.
Because that is generally saved in normal Schwarzschild, right? When this switches, the other one switches back, right? So effectively you maintain one time.
Yeah, but here, of course, if you take R less than B0, then the whole thing is not defined. And the reason why it is not defined is because of the choice of the R coordinate here. Okay. You can make it something which is smooth, where the coordinate runs from minus infinity to infinity by just going over to the proper radial distance. And there you will have the L coordinate, which is perfectly fine.
No, okay. Because I mean, it would be exotic thing. That's what I was a bit curious to know. Okay, thank you.
Yeah.
Okay, so there is a question. Amitabh,
Sayan, can you hear me, Sayan?
Yeah, sure.
So you showed this two metrics where they were related. One was black hole, one was wormhole. They were related by this double analytic continuation.
Yes. Yeah.
Do you know if it is possible to write a complex metric which interpolates between the two?
No, I don't know. It could be possible actually. Yes.
But this construction that you are giving, you think this construction can be adapted in some way such that such a metric can be written?
I don't know. It could be possible. I don't know. But even independently, what I found was independently, these two metrics have their geometric properties are identical to a large extent. Okay. The scalars, for instance. Okay. The analytical continuation is fine when one can relate the two. That's okay. But even otherwise, if you look at the metrics, they have a large number of identical properties. Okay. So, but then it also happens there are properties which are not identical, like their Einstein tensors are different. And their geometric characteristics, of course, are different because one can have a horizon, the other doesn't have a horizon. So those things are important, but it's interesting, as you said, that if you could write a metric itself, is a complex metric and which has its limits as these two. Yeah, that's a good point actually. Thank you. Yeah.
Thanks.
Thank you very much, Professor Kaur, for a very nice talk. Next speaker is Chetana Pal from Isaac Kolkata, and she shall be talking on
I'll just unshare.
Approach to compute conductivity of wave holographic superconductors. So, Chetana, please share your slides.
Hello?
Yes. Please,
Yeah, I'll share my slide. Is it visible? Hello?
Yeah. Okay.
Okay. Should I start?
Please start.
Okay. Good afternoon, everyone. Today I'll be talking about the conductivity of P-wave holographic superconductor, and I would like to mention Diganto Padai has collaborated with me in this work. So I'll start now. Here is the content of my talk. In introduction, I will briefly discuss about the history and motivation and the holographic principle, and then I will discuss the key features of holographic superconductor. Then we'll construct the gravitational dual for p-wave holographic superconductor and go on about analyzing the system around critical temperature. Then, as we want to look into the conductivity of the system, we will analyze the system in low temperature limit. Then, finally, we will discuss the conductivity at low temperature. In this last three sections, I will briefly discuss about the analytical prescription, and finally, in summary, I will summarize the results, and we have also done some numerical analysis, so we will compare the analytical results with the numerical results. Okay. Introduction. History. So in 1986, Penrose and Muller first discovered the high-TC superconductors. One of such example of such high-TC superconductor is cuprates, and the critical temperature is about 134 Kelvin. And these are strongly coupled system, and pairing mechanism for such strongly coupled system is not well understood. So, holographic superconductor provided us with the alternative tool to understand such high-TC superconductor. And holographic superconductors can be considered as an application of ADS-CFT correspondence or holographic principle. And it was first proposed by von Malvasena in 1997, and it was originated from string theory. So here is the conjecture. States that weakly coupled gravity theory in ADS T plus 1 spacetime is equivalent to a strongly coupled conformally invariant quantum field theory in one less dimension, that is CFT-T. This is also known as gauge gravity duality. And the name holographic principle suggests that if one looks at a two spatial dimensional superconductor, we can see a three-dimensional image. So here is the objective of this talk. We will construct a gravitational dual for p-wave holographic superconductor, then study the conductivity in superconducting phase. We derived the expression of frequency dependent expression for conductivity, and we will show that the DC conductivity becomes infinite. And then we will compute the energy gap, and also we have computed the ratio omega g by Tc, which roughly comes around 7.9 plus minus 5 for strongly coupled superconductor. Then we compare the analytical and numerical results. Key features of holographic superconductor. Here is the ADS-CFT dictionary. In the left-hand side, we have superconductors that is described by conformal field theory, and the right-hand side we have the gravity description. So in temperature in CFT description is equivalent to the Hawking temperature in the gravity side, and the condensation operator on CFT side is described by the charge field coupled to gravity, and the charge density and current density is described by the gauge field in gravity side, and the phase transition for the superconductor is described by the black hole instabilities in gravity side. By black hole instability, I mean there will be a static non-zero field or here outside the black hole below a certain temperature, but there will be no here above the critical temperature. Now the constructing gravitational dual. For our analysis, so as I discussed before, we need a black hole that is asymptotically ADS to describe a holographic superconductor. For our analysis, we have chosen this planar ADS 3 plus 1 Schwarzschild black hole, and the metric is given by equation 1, where the R plus is the horizon radius and the Hawking temperature is T is given by equation 2, that is T equal to 3R plus by 4 pi. Okay. So one of the simplest example of p-wave holographic superconductor is given by Einstein's Young-Mills theory, and the action for Einstein-Young-Mills theory is given by equation number 3 here. So this lambda is negative cosmological constant, and if A mu nu is the field strength of Young-Mills field strength, and A mu is the gauge field, and sigma A's are the generator of SU2 group. Next, let's consider this following answer. where this AT component phi r is the U1 gauge field, and the psi r, that is AX component psi r, that is the charged field. And the condensation of this charged field break the U1 symmetry that leads to a phase transition. Now, I will be considering this coordinate change that makes the equations easier. So z equal to r by r plus. So next we have in equation 5 and 6, I have written down the equation of motion in z coordinate. And as we can see, these are two coupled differential equation. Next we will go on to, okay, so the boundary conditions. Boundary conditions at the horizon, that is at r equal to r plus or z equal to 1, phi 1 equal to 0, and psi 1 is finite. And at the boundary, z tends to 0, the field phi and psi are described by these equations 7 and 8, where mu is the dual chemical potential and rho is the dual to charge density. And we have done this analysis where we have chosen psi 0 equal to 0, and for that psi 1 is related to the expectation value of the condensation operator O1. So we can write this psi field like this, and this fz now f0 equal to 1 and f prime is equal to 0 at the boundary. So next we will analyze our system around critical temperature. So around critical temperature, psi z is 0. So it is easy to decouple the coupled differential equation, and we can easily obtain phi z, and then we recast the equation of motion for psi in Sturm-Liouville form and obtain the and where the eigenvalue is lambda square, and we can obtain the relationship between critical temperature and charge density that is given by equation number 10. And Tc equal to 0.1239 square root of rho. Okay, now we'll analyze the system in a low temperature limit, as we want to look at the conductivity. So for low temperature limit, we cannot decouple the differential equations so easily. So instead, we choose here this scaling z equal to s by b. That will corresponds to low temperature, that I'll discuss later how. And this b tends to infinity. So I have rewritten these two differential equations in terms of this new coordinate s, and we'll try to solve them. And we'll try to solve them iteratively, and we'll start with fs equal to alpha by s, where it's the behavior of fs around s greater than 1 or z greater than 1 by b. And we have chosen b to be this factor here. So as you can see, as r plus tends to, as b tends to infinity, that means r plus tends to 0, which in turn implies that T tends to 0 from the relation of Hawking temperature. So r plus tends to 0 means T tends to 0. So indeed, if we take b tends to infinity, that corresponds to low temperature limit. And now we obtained the first order solution for phi, and here this alpha and c are the constant which is to be determined. Okay, so this equation 13 is the equation of psi that I have written down after putting the first order solution for phi and psi. So we aim to solve this equation in two different approaches. One is Sturm-Liouville approach and direct approach, and then we'll compare the results. So here is the behavior of phi and psi that is obtained from Sturm-Liouville approach, and here is the behavior of phi and psi that is derived from direct approach. And we can also compute the critical temperature and condensation operator relationship. To do that, we take the equation of phi that we have, we take the solution for phi that we have obtained, that is basically given by equation 14 and 16, and compare it to the boundary behavior of phi, and we can obtain this relation, condensation operator and critical temperature. And here is a table. In this table I have shown these comparisons for alpha, C and xi obtained from two different analytical approaches, direct method and Sturm-Liouville approaches. So these are pretty close. And here is the numerical results. For numerical results, I have plotted this condensation ratio of condensation operator and critical temperature versus T by Tc. So when this T by Tc ratio is around 0.09, we numerically obtain this coefficient xi, it's 9.5, and analytically we have obtained this to be 9.6 when we consider the low temperature limit. So these are pretty accurate result if we consider this T by Tc to be 0.009. Okay. Next, here is the plot for phi, and this is the plot for psi, or obtained from two different approaches. The orange one is from Sturm-Liouville method and the green one is from direct approach. And the next I have plotted phi and in two different approaches. And now I'll discuss the conductivity at low temperature. So to study the conductivity on the boundary, we introduced electromagnetic perturbation in the bulk, that is, and we have chosen this particular answer given by equation number 18 here. And the analysis is done on probe limit. That means we do not consider the effect of this gauge component on the metric. And this equation 19 is the equation of motion for chosen answers. And here we can see this. Here is a psi sitting here, so we will be substituting the psi that we have obtained in low temperature to analyze the system. And the boundary behavior of the gauge field is given by this: Az equal to A0 plus A1 by R plus into Z. Next, we attempt to solve this field equation for A, and we switch to the tortoise coordinate and write down the equation of motion, and that is given by equation 20. So as we can see, at the horizon, psi equal to 0, hence this V is 0, and we get the solution at the horizon, that is, and we consider the ingoing boundary condition here, and A is equal to exponential minus I omega R plus, and this is the solution of A at the horizon. Now we will solve the field equation for A in three different approaches: direct approach, then self-consistent approach, and then we define the solution using perturbative approach. So in direct approach, we start with this Az here. The first factor is the solution at the horizon, and we multiply it with by Gz, and we will try to find out what this Gz is. And as I said earlier, we use the solution of psi obtained in low temperature, and this is the expression of Az at T tends to 0. And then is the definition of conductivity is given by equation 22. Now as we have obtained Az, we can obtain the expression for conductivity, which is given by this equation here. And next, here are some results at low temperature and low frequency. The imaginary I have written down the imaginary part of conductivity here, the real part of conductivity, and the band gap Eg, that turns out to be 0.3631 square root of O1, and you can also compute the ratio omega g by Tc, omega g is the corresponding frequency of this band gap energy Eg, and that turns out to be 7.0894. And now self-consistent approach. Here we replace this V with average V in a self-consistent manner and write down the solution. And so we aim to determine this average V, which is given by this here, and the conductivity, the definition of conductivity is given by equation 23. And so using this self-consistent approach, we have obtained the conductivity for the entire frequency range. So I have written down the expression in high, intermediate, and low frequency range. And here as you can see, low frequency range, we obtained imaginary part of conductivity to be 0.489, and from a direct approach, it turned out to be 0.46, around 46. So that is also a good estimate from two different approaches. And now I have taken this delta V as perturbation here, where this factor here, alpha O1 by root 2, this is the average V in intermediate frequency range here, this factor. So now we obtained and we use the 0th order solution of AR and AR star, and then obtain the solution expression for AR star. And this is the definition of conductivity written in tortoise coordinate, and this is the expression of conductivity obtained from this perturbative approach. And as we can see, we have written down the conductivity in terms of omega by Tc. So that all the other parameters are known.
You have 2 minutes more, Sujita.
Okay.
Please
So
type.
yes. So here I have plotted the real part and imaginary part of the conductivity. The green one is the analytical plot and the blue one is the numerical plot. And for numerical plot, I have taken T by Tc, this ratio to be 0.09. And now comments on the plot. As we can see, this as omega tends to 0, this imaginary part has a pole, and from Cramer's conic relation we can conclude that if imaginary part has a imaginary part of conductivity or has a pole, then that means in the real part of conductivity there is a delta function at omega equal to 0, and this delta function signifies infinite DC conductivity. And at t tends to 0, real part of conductivity vanishes for all omega less than omega g, and a gap appears. And omega g by Tc turns out to be 7.4, and indeed for strongly coupled superconductor, this ratio turns out to be around 7.9 plus minus 5, as I have mentioned earlier. And here is a sample, and for this sample, this is a high Tc superconductor, and this ratio of omega g by Tc, that turned out to be 7.9 plus minus 0.5. And if we talk about the weakly coupled superconductor that described by BCS theory, this ratio turns out to be approximately 3.5. So, okay. And now I quickly summarize the results. So, we have analyzed the system around T equal to Tc and obtained the charge density and critical temperature relationship. And here is this is the xi analytical and xi numerical. And then we have analyzed the system in low temperature and obtained the condensation operator and critical temperature relationship. So here is the this is the analytical result, and turns out to be 9.7, and the numerical is 9.5 for this coefficient xi. And we introduced perturbation in the bulk to study the conductivity. analytically obtained the expression for conductivity at omega equal to 0. We have shown that DC conductivity becomes infinite and obtained a gap in optical conductivity, and at t tends to 0, this omega g by tc analytically turns out to be 7.4, and also numerically, if we consider this t by tc ratio 0.09, then it turns out to be 7.4. So this is the end, and I would like to thank Dr. Sunandan Gangopadhyay for his guidance and Diganto Pare for his collaboration. Thank you.
Okay, thank you very much. Let's thank you, Stephen, for a nice talk. So, time for very quick question.
So I have two basic questions. One of them is, so in your one of the points in your motivation was that the pairing mechanisms of high superconductors are not well understood. So does this approach for using this again gravity duality to find out the conductivity tell you anything about the qualitative features of the pairing?
Actually, I cannot hear you properly. Can you repeat that question once again?
Yes. Can you hear me now?
Kind of, yes. I
Can you
could
hear me now?
understand the. Yeah.
Okay. Okay, so my question is, does this approach, the use of great gravity duality to find out conductivities, tell you anything qualitative about the pairing mechanism, which was one of the points in your motivation, about the mechanisms in high TTC superconductivity? So what does it tell you about how the pairing works?
Yeah. Actually, I don't know that answer. How does it describe the pairing mechanism? But we can definitely show some features that superconductor shows, like for example this superconductivity or Meissner effect or phase transition. But for now, I'm not very sure about the pairing mechanism. I mean, I don't know, so I have to look into that.
One comment to this check. Actually, from this approach does not give you microscopic theory about the pairing mechanism. So you cannot say anything from this particular gravity description. If you really want to know the pairing mechanism, then you need to have a quantum gravity kind of theory, which can actually tell you something about the pairing mechanism. But it's not clear.
One more quick question.
Yes.
So this was done for a P-wave superconductor. So for instance, if I want to do for a D-wave or a S-wave, how does the corresponding gravity action change?
Like for example, if you want to.
So here you have Samuel's action, right? So
yes.
How would that change for a D-wave or S-wave?
For S-wave, usually yeah.
Quickly, we are running out of time, so we should. Or maybe you can discuss later.
Yeah, there are like a lot of paper is available where you can look into the action. It's just we add an external matter field, and we can use just simple F mu action, that is Maxwell action coupled with the matter field. That is the action for S wave along with the Einstein part. So
okay, thank you, Shashakana, for your nice talk.
Thank you.
Once again. Next talk is by Dr. Vermonts Jain, and this is also a contributed talk of 20 minutes. And we shall be talking on 5-dimensional partition functions at large N and black holes. So, Vermonts, please share your slides.
Yeah, I'm trying to do that. Are my slides visible?
Yeah. And you are audible on both screens.
Okay. So the title slide is visible, right?
You cannot, please unmute yourself. Mute yourself. You have to mute yourself.
Okay, so I can start now, right?
Yeah, yeah.
Okay, yeah. Thank you for the introduction. So, as my talk's title suggests, I will be talking about some 5D partition functions in a certain limit. This is a vast and rich story spanning across dimensions, which I won't be able to do justice in this short talk. But fortunately, this story finds some motivation from the ADS-CFT correspondence, which is fitting since this talk is part of this interesting conference on future trends in gravitational physics. But sadly, that motivation will be all of the gravitational content of my talk, as I will be focusing purely on the field theoretical side of the ADS-CFT correspondence. This talk is in most part based on my 2020 paper with Marco Scricigno. Let me continue. So I will basically talk about a result relating two types of partition functions in 5D, one on S5 and one on S4 cross S1, which is also called superconformal index. And after we are done with that, I will just flash a slide containing results for other partition functions near the end of my talk from my latest paper in the last year. So we start with the familiar setup. We have ADS-CFT correspondence, we have ADS black hole, and holography predicts that there are certain universal relations for certain quantities for the CFT. And by universal, I mean that these relations hold regardless of how the black hole is embedded in string theory or M theory or whatever you have. So it doesn't depend on the microscopic realization of the black hole. These are universal in that sense. So let me specialize to odd dimensional CFTs, and I saw two basically in odd dimension there are only two possibilities, 3D and 5D. So I saw the universal relation that are predicted from holographic. So let's just focus on 3D part. So on the left hand side we have a partition function on S2 cross S1 that is also called a superconformal index in 3D. On the right hand side we have FS3, which is called free energy, and it is defined as negative logarithm of the partition function on S3. Right, and the proportionality constant is basically just a geometrical factor depending on phi and omega. Phi is basically just proportional to omega, and omega is a deformation parameter of the S2. The same structure holds for 5D also, that this proportionality factor is just the deformation parameters of S4. And on the left hand side we have S4 cross S1, the superconformal index on 5D, and on right hand side we have FS5 as the other factor. These FSDs are called free energy, and they are very important quantities in the odd dimensional CFTs because they measure the degrees of freedom of the theory. Basically, there is something called F theorem, which basically tells you that these Fs are monotonical. They display monotonic behavior across RG flow. So that may remind you of something called a C theorem in 2D. And in fact, in the 2D also you have a similar feature of the torus partition function on one side, and the central charge which has a similar behavior as F in order. So central charge also measures degrees of freedom. It is monotonic across RG flow, and the proportionality constant is again a geometric, which is related to radius of S1. So if you know about a 2D Cardi formula, these formulas in 3D and 5D do look like Cardi formulas. So so now the question again lingers in the mind: why are these universal relations? And it turns out that this is consequence of the universality of the Bekenstein-Hawking entropy formula, which is universal because it is derived from a weakly coupled semi-classical analysis of the gravity. So let me just make that a little bit more precise. So let's review that ADS-CFT correspondence in its strongest sense is an equivalence between CFT and string or M theory on background involving ADS spaces. Mathematically, that statement can be written as partition function of the SCFT is equivalent to partition function of the full string theory. But this strong statement is not that useful because neither of these quantities can be computed exactly. Right? So we take a sort of a weaker version of the statement and look at weakly coupled gravitational theory, which reduces string or M theory to just the relevant supergravity theories, and look at the strongly coupled field theory on the other side. So this SCFT is strongly coupled, and the partition function of string theory M theory just reduces to the Sugra action. So we will look at just the Euclidean version. So we have IE as the Euclidean action. So this can be repackaged as log of ZCFT as minus IE. Let's take a concrete example in ADS6 because I'm going to be talking about 5D SCFTs, and in 2008, Chow and recently Kasani Papini, they discussed these black hole solutions, which are charged and rotating black holes in ADS6, and they found that the on-cell action for the SUGRA, for this ADS6 geometry, turns out to be this action. And if you use holography, this Gn part can be related to FS5, the free energy of the CFT on the S5, right? So this looks similar to what I showed, the universal relation that I showed in the earlier slide. By doing a transform. So now we can also look at the holographic consequence of that. So if we know minus IE is the partition function of the CFT, the proper thing like in for 5D, it should be S4 cross S1 partition function. Then that means if we know the partition function of the 5D CFT, we basically know the black hole entropy by this Legendre transform. We don't actually have to compute the gravity action, because, and that's also I mean, both these things are complicated, but as I will show, L and Z CFT computation is a little bit easier, because as of now there is only one computation with this particular black hole existing for ADS6. There are no general solution with more charges available in the gravity literature, but as I will show, for Z CFT you can compute in quite generality with different charges and so on. So yeah, so that's the story. That's the main point of the talk, that we will be focusing on the CFT on S4 cross S1, and we will see how this relation can be derived and what that consequence is. So let's move to CFT. And as I already mentioned, we will focus on two quantities, the S5 partition function and S4 cross 1 partition function for 5-dimensional supersymmetric gauge theories. And I can't give you the full derivation, but I will just give you some facts that using localization, these two partition functions can be computed exactly in the large n limit, where n is the rank of the gauge theory, because localization reduces the infinite dimensional path integral to finite dimension matrix model. And just at outset, these two partition functions have very different matrix models. There is no simple relation at finite n, but when we take the large n limit, a universal relation emerges, and it is a much more general universal relation. But if we take this specific universal relation that I will mention, that the condition which I will mention later, we will obtain the Cardi-like formula which have been predicted from the gravity holographic analysis. Right, and we can do much more from these 5D theories. We can reduce these 5D theories on Riemann surface, and then we have an effective 3D theory. And again, for these effective 3D theories, we again obtain the same, the expected 3D Cardi formula of the 3D theory. But we don't have time for that, so we'll just focus on 5D theories. So how are the 5D theories built? They have basically two main ingredients. One is the vector multiplet, one is the hypermultiplet. Vector multiplet obviously has the vector a mu. It has a real scalar sigma. It is the only important field in under fields. Then the fermions. In hypermultiplet, you have 4 bosons phi and again 4 fermions. So this is the typical setup of these of the fields that are that can be used to construct 5D gauge theories. This group theory dimensions are also given, but I guess that's not that important right now. So yeah, given those vector and hypermultiplets, you can construct 5D gauge theories, and there are you can construct a large class of gauge theories which have UV completions at 5D SCFTs. And these 5D SCFTs can have ADS6 duals in both in either type 2A or type 2B string theory. And there are lots of examples. So let me give you just one example. So in type 2A, there is a theory which is called Seiberg theory, and the matter content can be represented in this quiver diagram. So quiver diagram is basically made of nodes and lines. The lines denote the hypermultiplets, and the circles denote the vector multiplet, and these n's basically mean the gauge group. So in this case, the gauge group is USP2n, and this is a flavor group SO2NF. And this hypermultiplet is in antisymmetric representation. This is a fundamental hypermultiplet. So you can construct a large class of theories in 2A, and all those theories have FS5 proportional to n5 half. So let me just clear this up. So n5 half is the crucial number here. The free energy scales as n5 half. This was calculated a decade ago, and this is a quite simple calculation. But in 2b, the story is not that simple. This calculation is quite non-trivial. But in a couple of years back, Uleman did that, and it was found that these theories are long quivers. They don't just have large n kind of gauge group. They have all the smaller gauge group also, like SU2, SU3 up to SUn. And these theories scale as n4. So they are a different class of theories in 5D. And for both these, you can compute S5. The computation for 2b is quite non-trivial. And the point of my talk and my work last year is that you can actually do this computation in a unified manner without referring to which theory you are talking about. You can do it in general, and it will hold for both these classes of theories and in general. So, and yeah, we will use this gauge theory description to compute RG invariant partition functions via localization, so that what we compute is valid for the SCFT, valid for the 5D SCFT. Right. So let's look at the S5 partition function. The S5 the squashed S5 can be defined by this equation, and that is sort of obvious. We just have 3 complex coordinates in 6 dimension, and then you can have 3 squashing parameters, omega 1, omega 2, omega 3. The partition function that I will show in next slide depends on a few parameters and variables. The parameters are Q1 and Q2, and they are basically exponentiated ratios of these squashing parameters. Right, and there's 3 sets of them. And U is basically sigma in disguise, and the whole path integral has been reduced by localization or to this real integral over the sigmas, like over minus infinity to infinity. This is a real integral. And again, there is 3 sets of x's which the partition function will depend on. Right? And the hypermultiplets can be given masses, and that is by thinking of having a background vector field with this sigma playing the role of the mass for the associated vector hypermultiplet. So in practice, you can just shift sigma by m to get those masses if needed. And the partition function will be written in terms of this double Pochhammer symbol, which is a double product given by this, like 1 minus z q1 q2. So given this function, you can write the one loop contribution to the partition function. There is an integral over these u's. There are these Pochhammer symbols. The top contribution is from vector. The bottom contribution is from hypermultiplet. The explicit symbols do not matter much at this point. And I also should mention that this is only one loop contribution. There are instanton contribution and classical contributions which are subleading in large n. Since I am interested in this large n limit, I won't be showing those. So apart from these rational function, there is this exponentiated function, which is basically a cubic polynomial. This is denoted by B33, which is a Bernoulli polynomial, and it's cubic. So u's, as I told you, are just the scalars, and alphas and rhos are the roots and weights of the multiplets. So rho represents weights of the representation in which the hypermultiplet is. So you sum over all possible vector multiplets and hypermultiplets to get this relation. Right. And it turns out that now, if you do a large n analysis, the dominant saddle is such that the u is imaginary. So u is basically I sigma, and sigma has to be large. We are doing large n limit, and in that limit, this ratio just vanishes. I mean, this is subleading. The only thing that is relevant at large n limit is this psi function, and it's a cubic polynomial. So I can just rewrite that in some simple notation, in a very suggestive notation, that there is a contribution from vector, there is a contribution from hypermultiplet, and it will be a cubic polynomial. So let me show that cubic polynomial. So the u's I scale by this factor, and it turns out that all the geometric thing just factors out of those functions, vector and hypermultiplet contribution, except that linear part has this slight dependence on the omegas. But the cubic part is just opposite, and this is opposite, but there is this still remaining in the linear part. And it turns out that those type 2A and type 2B dual SCFTs that I showed you, those have such a matter content that this part either cancels away or is subleading, right? So that means for all the SCFTs of interest, we just have a factorization of the geometrical factors, and the squashed S5 free energy is related directly to the round S5 with just this trivial scaling of the mass parameters in the free theory. So it's just a trivial rescaling, you can rescale them away. So the FS5 has no omega dependence, the squashing parameter just go. So this factorization will be crucial in trying to derive those universal relations. So this is one part of the story. Now let's go to the other partition function, which is the superconformal index, or the partition function on S4 cross S1, where S4 can again be deformed in with two parameters, epsilon 1 and 2. R is the radius of S1, and but again we can use localization to evaluate this partition function. And it turns out here we just need two sets of the variables. Q1, Q2 are still similarly defined. X's here are U. So U here is different. It is a complexified stuff. It's sigma plus I. Since there is an S1, the gauge field can give a holonomy around S1, and that is the actual gauge variable. So this complexified thing is what we call U, but the notation is still similar, like X and Y. The analog of M in S5 becomes a nu here, so we denote that by nu. And the again only the one loop partition function for S4 cross S1 can be written like this. So now we have just a square here. Earlier we had like product of three Pochhammer symbols, but now we have this two. And again we have a psi hat function here, but this psi hat function is a little more complicated for this partition function. It's a ratio of gamma function, and gamma itself is a ratio of a double Pochhammer symbol. So it's not a simple polynomial at this point. So that's the tricky part, and it was a lot of time since it was simplified and we could derive that universal relation. But anyway, so that's the whole point. We can do a similar Larsen analysis here, and it will turn out that this ratio again is subleading. Only this psi with this ratio of gammas contributes at Larsen. As I said, that this is again the similar story at Larsen. Only sigmas going to plus minus infinity contribute, just like a complicated cubic polynomial in case of S5. But no worries, we can cover some mathematical literature and find how to take Larsen limit of gammas. And it turns out that after 2-3 steps, gamma indeed reduces to a B33 with a factor 3 here. Earlier, if you remember, there was a 6, but we have a nagging linear piece again left over. But that nagging piece is not that important because it is irrelevant for the same reason that F omega was irrelevant for ZS5. So if we have the same kind of quiver, then this term is not contributing, and as you might expect, the integrand is just square of what we had for S5. If we identify the parameters carefully, so the omega of S5 are related to S4 cross S1 parameters like this, so R inverse, and the masses of S5 are now related to these complexified nus of S4 cross S1. With this identification, the integrand of S4 cross S1 is a square of the integrand of S5. And once we take the saddle point approximation, which is a tricky business, like for 2A it's easy, for 2B it's hard, but that doesn't matter because whatever saddle you choose, if there is just one dominant saddle, you do away with the integral and the whole partition function has the same feature. Now, if integrand was square, the whole partition function is also now a square. So Z of S4 cross S1 is a square of ZS5 with those parameter identified. So now that leads to a interesting consequence. We can take a log and we get this. So S1 is proportional to S5. So this is almost starting that I showed you earlier, but this is much more because now we have these extra m's hanging around here. The universal relation did not have an analog of m, and that will become clear in a while. But this relation already extends a number of results in the literature. So around 2 years back, people had a Korean group had derived this relation for type 2A dual, and in the additional condition that these epsilons are small. But what we have done is derived only for large n limit. We have not put any condition on epsilon 1. So this is a much more general result. And the way we have derived it is much more general that it applies also for 2B duals. So now let's.
Time is almost up.
Okay, so yeah, I'm almost done also. So let me just show this last result that we can take the universal limit by setting the nus and m's to 0 and then redefining these epsilons like this. And in fact, you get the exact relation for this curly phi, which was related by this, and you get the exact holographic prediction from the SCFT calculation. And as I said, this relation holds for both 2a and 2b. It's a quite general result. So anyway, so I will just splash here a slide where a lot more partition functions can be computed. The sigma g partition functions are are given in terms of another object called Tutush's superpotential, which is related to S5, and then this log z itself is related to the W and derivative of W. So anyway, this is sort of a general structure. And as I said, these two relations I've already talked about. And if you reduce 5D to 3D, you can again, if you know the sigma g, it's basically a 3D relation, which is also valid for 5D relation. So anyway, so I will end there. There are lots of things one can do. And yeah, if you have questions, I can take. Otherwise, I will leave it here. I guess I'm out of time.
Thank you so much for a very nice talk. So, if there are questions?
Yes, I have one question.
Yes,
Yeah.
please.
Thank you, Dharmesh, for the nice talk.
Yeah.
So this Korean group that you mentioned, so they were able to make connection to this type 2a black holes, and they showed that this free energy calculation matches with the on-shell action of this Chow black holes that you mentioned in the beginning. Can you hear me?
Yeah. Yeah, your voice was not clear in the middle. Now I can hear you. Can you repeat your question, please?
Yeah, no, I was saying that this Korean group calculation that you mentioned,
yeah,
they were able to make connection to this Chow's black hole that you mentioned in the beginning, type 2a.
yes,
Chow.
yes,
Yeah.
yes.
So actually, I wanted to know what kind of black holes you are trying to make connections with type 2b calculation. I mean, it's not clear.
Oh, so I mean, I am not doing an actual black hole calculation here. I'm just saying that these.
Yeah, no,
So,
that I understand you are not doing, but what kind of black holes in type 2b you will try to make a connection?
Yeah, so those type 2b black holes are constructed by these people in 2016. So these are in like I'm sorry, I don't quite remember all the details right now, but this is a proper. I mean, these black holes do exist. They have been constructed, and what calculation I have done for FS5 says that the relation that holds for type 2a also holds for 2b, the way we have derived that relation.
Okay. Well, okay. We will discuss later. Yeah.
Okay.
Please, so thank you very much, Dharmesh.
Yeah. Okay.
Talk.
Thank you.
Once again. The next talk is by Subrat Raju of ICTS Bangalore, and this is an invited talk of 40 minutes, and we shall be talking on failure of the split property in gravity and the information paradox. So Subrat,
thank you. Thank you.
It's all yours.
Yeah. Can you hear me clearly?
Yes.
Okay. I'll just start sharing. 1 second. Can you see this also?
Yes.
Okay, thank you. Okay. Thank you very much to the organizers for inviting me to this workshop, for organizing this workshop. I'm sorry we couldn't have this workshop in person, but hopefully next time the workshop is organized, we will get a chance to do this all in person. So before I start my talk, I would just like to take a minute to acknowledge my collaborators. So I'm going to speak about a story that started with some work with Alok, Siddharth, and Pushkal in this paper now almost a couple of years ago, and another paper that we've been writing up for some time and hopefully will appear in a few weeks. And then a follow-up that we wrote with Chandramoli and Olga, and another follow-up with Chandramoli, Olga, and Victor. And then a couple of papers that we wrote with what we call the group of 7, which is Hao, Andreas, Carlos, Lisa, Marcos, and Sanjeet. And then these 2 papers that I wrote And in fact, this talk will be based largely on this last paper that appeared in October last year, which is in red if you'd like to see more references. So let me just try and give you the main point of what I'm going to say. So the main point of this talk is going to be that unlike non-gravitational theories, quantum gravity does not support what are called split states. And split states are those which differ inside some bounded region, but they look exactly the same outside. And in non-gravitational theories, one can find such states, but one cannot find such states in gravitational theories. And I'll try and explain why several versions of the information paradox tacitly assume that gravity does have this split property because it's something so familiar, and how removing this assumption provides a rather robust resolution to this class of paradoxes. And one perhaps colloquial way of saying this is that information is always outside the black hole in a theory of gravity for sufficiently fine-grained measurements, but I'll make it more precise as we go along. And I'll also speak a little bit about recent work on the Page curve that has attracted a fair amount of attention in the high energy community. But I'll point out that the idea that the entropy of the black hole radiation should follow a Page curve relies in fact on precisely the same incorrect assumption. And it is for this reason that the Page curve computations that have been performed have not been performed in standard theories of gravity, but in non-standard theories of gravity, where the graviton has a mass and the Gauss law does not hold. And in a standard theory of gravity, as I said, I think that a better way to understand the resolution to these paradoxes is in terms of the failure of the split property. So I'll explain these ideas as we go along. So before I start saying more technical things, let me just try and give you maybe a 10-minute overview that's appropriate at a very general level. Okay? And then I'll say more specialized things. So in quantum gravity, the theme of what I'm going to say is that there's a very unique feature of quantum gravity in terms of how it localizes information. And that is that information that is present in the bulk of a Cauchy slice is also available near the boundary of the slice. So you might have some bits or some qubits which are living in the bulk of the space-time, but that same information is also available to sufficiently fine-grained measurements in the boundary. This is very different from the way we usually think of how information is localized in quantum field theory. So let me just remind you, in quantum field theory, we usually assume that you can prepare states which look like the vacuum outside. This is a cartoon, but you can write down a wave functional which coincides with the vacuum outside some region, and inside some region there is some excitation or some bump. And what is more, we can think of a second state which also looks like the vacuum outside this region, but the shape of the bump inside this region has been changed. And this is key to our idea that information is inside this bounded region, because information about whether the bump is of this kind or of this kind is not available to an observer outside, and the observer has to visit that region to obtain that information. And that's why we say information is inside this region, a bounded region, but not outside. Now, the point of what I'm going to say is that in a theory of gravity, one cannot prepare states like this at all. So first of all, you cannot prepare a state which has an excitation and which looks like the vacuum outside. But it's more than that. If you change the form of the excitation, this is even true in classical gravity. If you put some mass, you have to change the gravitational field far away. But as a result of quantum effects, in the classical theory, you can move the mass around while keeping the gravitational field far away unchanged. But as a result of quantum effects, I'll try and explain why if you change the excitation inside, you have to change the form of the gravitational field far away. And this is a very unusual effect in terms of how we think about how information is localized, and that is why it is often overlooked. So before I give you some more results, some more precise statements, let me try and tell you, why would you believe that something like this exists, right? I'm saying something which sounds so unusual. So why should you even believe it's true? So here is the physical intuition, if you just want to think about the physical intuition. So, let me remind you that, of course, the moment we go to quantum mechanics, you might start worrying a little bit about localization because, we just have the uncertainty principle that tells us if you have a definite momentum, and in theory of relativity, energy goes with momentum. So if you have a definite energy, then the wave function of your excitation is delocalized everywhere. That's just the basic uncertainty principle. Of course, this doesn't usually stop us from localizing excitations. So, when we say we have a particle which is localized in some space, we say that, well, the way we do it is we take a wave function of some energy and add to it a wave function of at another energy with the right phase and a third one and a fourth one. And if you do that, you can ensure that you have destructive interference outside a bounded region and constructive interference inside a bounded region. And that is what we mean by a localized excitation. Now, what is different about gravity? So what is different about gravity is something very familiar. It's the humble Gauss law. It's the fact that the energy can be measured at infinity. So that's how we know the energy of the sun, right? We can measure the energy at infinity. In fact, in general relativity, the only definition of the energy is by means of the integral at infinity. And the expression you see in front of you is just the standard expression for the EDM Hamiltonian in the theory of gravity. Now, how does this affect this issue of localization? The way it affects the issue of localization is that if one now goes back to this game of where you try and superpose particles of different energies, you see that every time you have a wave function with a given energy, that comes together with a certain tail, which must go out to infinity just because it has to satisfy the Gauss constraint. And now if one tries to play this game of superposing different energy states in order to get a localized excitation, you find that every energy eigenstate that you write down is correlated with a degree of freedom in the metric which lives at infinity. And this degree of freedom is, it's genuinely a different degree of freedom. And so while you might be able to ensure the destructive interference of this excitation if you did not have these tails outside, the presence of these tails prevents interference outside a bounded region. And as a result, and I'll make this a little bit more precise, correlation functions of the energy and other observables at infinity carry information about the state inside. So that is the physical intuition for why we expect an unusual property of this kind in gravity. Okay, so I'll now make this a little bit more precise and let me try and give you some more results. I don't have time to go into proofs, but I'll state the results that we know. So here's the statement that we can make, which is a very robust statement about a four-dimensional asymptotically flat spacetime. The statement is simply that if one thinks of the set of all massless particles, then information about all massless particles, the state of massless particles, is available near the past boundary of future null infinity. So let me remind you, this is a Penrose diagram, and this is future null infinity, Scri plus. And the past boundary of future null infinity is this little red region. This is how it looks like if you go to one more dimension. And the claim is all the information is available. You don't need to make measurements on all of null infinity, all of Scri plus, but you can get away by making measurements only on Scri plus minus. Everything I say has an analog for past null infinity. So the information is also available on this little orange region, but just to avoid duplication, I'll keep talking about future null infinity. Okay, so let me just try and make this a little bit more precise. So, what are the observables? So if you think of asymptotically flat spacetimes, because we want to talk about quantum gravity, we don't say anything about what the metric does in the bulk, but we allow it to fluctuate, but it still makes sense to talk about asymptotic observables. And the set of asymptotic observables include basically the subleading tails of the metric, which go by the name of the Bondi news and the Bondi mass, and also subleading tails of other dynamical fields. Since we are talking about massless particles, you look at dynamical tails of other matter fields, and they also give you some observables on future null infinity here. And we are interested now in the algebra of observables near the past boundary of future null infinity. So if I take Y to be one of these set of observables, then in a non-gravitational theory, if one wanted to specify the state of massless particles, what one would need to do is specify correlation functions of insertions of these observables on all of future null infinity. That is going from retarded time minus infinity to retarded time plus infinity here. So you would have to tell me news correlators on all of this region. But in a theory of gravity, the claim is that it is sufficient to specify observables in this little red region for this range from u goes to minus infinity to minus 1 over epsilon. And this already contains all information about the state. So you see that there is information in gravity is squeezed into this region, which looks like a very small region compared to all of null infinity. It's a semi-infinite interval, but on the Penrose diagram it looks like a small region. And it's clearly in a non-gravitational theory, this would only give you a subset of observables, but in a gravitational theory, in this sense, flat space is holographic in that all information is available here. Okay, let me say a few things about this result. As I said, I don't have time to give a proof, but I'm happy to give more arguments, to give you more details if there are questions later. So this is a result that holds under non-perturbatively under rather weak assumptions about the UV theory of gravity. So we know the low energy theory of gravity. We don't know its UV completion, but provided this UV theory has certain rather robust properties, which is A, that the positivity of the Hamiltonian, and B, that the Hamiltonian itself remains a boundary term in the full theory, one can show that this result holds. So it's a rather robust result. And it's rather remarkable that one can obtain this result just by thinking carefully about rather low energy physics, but then understanding that some properties are robust and can be extrapolated to the UV theory without knowing the full UV theory or string theory in 4-dimensional flat space.
Can I interrupt with a question, please?
Sure, yes.
Yeah. So your Hilbert space, is there a distinction between gravitational quantum states and matter quantum states? Or here do you have only pure gravity, no matter?
No, we can have matter quantum states. So the set of observables that I included also massless matter. So you could think of a theory of gravity coupled to massless matter. And you would, of course, have the usual gravitational states, which you get by acting with a News tensor. So those are just gravitons. But in addition, you could have a state which had other matter excitation. So you could include photons, or just you could think of a theory with massless scalars, and you could include those as well. I'm not saying something about massive particles. That's something that we are working out. I could give you more details, but that's a slightly more complicated story. But for massless matter, there's no problem in including it.
Okay, thank you.
Okay, great. So now, perhaps a question that someone might have had is, I'm giving you this result saying that observables on the past boundary of future null infinity are sufficient. And that is the sense in which, information is available at the boundary of the slice. Because if you look back here, the Cauchy slice for massless particles is all of null infinity. And this is the statement that the information is holographic. It's stored in this red region. So now you might have said, okay, you're giving me some formal result, but I don't believe you. What prevents me from just writing down two wave functionals of this form? I'll just write down a wave functional, one of which looks like the vacuum and has some excitation in the middle, somewhere in the middle of null infinity. Or maybe I'll take a Cauchy slice and do it in perturbation theory about Minkowski space. And here's another wave functional. I'll just write down two states, and then you can give me whatever proof you like, but clearly you can't read off the form of the excitation in such states from infinity. And so that's a natural question that one might have. And the point is that, of course, in a quantum theory, not all wave functionals are allowed. So in a theory of gravity, the set of allowed wave functionals must themselves obey certain constraints. These constraints simply reflect the diffeomorphism invariance of the theory, and they go by the name of the Hamiltonian constraint and the momentum constraint. And the Hamiltonian constraint is also called the Wheeler-DeWitt equation. So one can show that if one looks at ADS perturbation theory, so now I'm switching to a result about ADS because in ADS we can control some infrared effects. So this is a weaker result. I'm giving you a result in perturbation theory, but it's more explicit. So one can show explicitly in ADS perturbation theory that two solutions of the Wheeler-DeWitt equation that coincide at the boundary of ADS. So this is ADS, it looks like a solid cylinder, and two solutions of the Wheeler-DeWitt equation that coincide at the boundary of ADS for an infinitesimal amount of time on this red band must coincide everywhere in the bulk. This is the statement that one cannot write down two states of the form previously. If one tried to do that, where you try to make something look the same outside and distinct inside, those states would not satisfy the Wheeler-DeWitt equation. And let me emphasize that you might have guessed that this is the case from ADS-CFT, but this result that I'm describing does not assume ADS-CFT. Rather, it establishes a perturbative version of holography for gravitational theory. So it shows that if we demand the Wheeler-DeWitt equation, then holography follows from the constraints, and it's not something that one needs to put in as an additional statement about the theory. Okay, let me try and explain once again. I can't give a full proof, but I'll try and explain, I'll try and sketch how we go about this argument. Okay? So the main point is that we are able to write down perturbative solutions to the Wheeler-DeWitt equation, which surprisingly have been studied less than we thought they should have been, even though the Wheeler-DeWitt equation has been around for 50 years. There's been surprisingly little work on perturbative solutions. And we were able to write down solutions to a particular integral of the Hamiltonian constraint. So the Wheeler-DeWitt equation is called an equation, but actually it's an infinity of equations. It's imposed at every point in space. But it's important, it turned out to be important for us to look at a particular integral. And these solutions had this form of the cartoon that I showed you at the beginning of this talk, where I said, you have some state of matter excitations, or maybe even graviton excitations of the dynamical degrees of freedom of the graviton. And this has to be correlated in a particular way with some degree of freedom of the metric at infinity, which is this red tail. So in the Wheeler-DeWitt context, we can make this completely precise in that the solutions to the Wheeler-DeWitt equation have to have this form. And we can explicitly construct both these matter wave functionals and these constrained solutions. And then we can lift these to a solution, or we can at least argue that these get uplifted to a solution of the full set of constraints. But this part of the solution that we can get explicitly is what's important. And then it's easy to show that if you take any mixed state in this that's made up out of solutions of these equations, then imposing the equality of these boundary correlators, which are correlators made up of the metric, that's this edge, and other degrees of freedom at the boundary, forces these two states to be equal. So this is the precise version of the cartoon that I showed you previously, where I said that, correlation functions of the energy and other degrees of freedom of the matter at infinity have information about the state in the bulk. And in this set of solutions of the Wheeler-DeWitt equation, one can show explicitly that these correlators at infinity completely fix the state of the theory in the bulk. Okay. So that is what I wanted to say about what we call the holography of information. Let me now move on in the second half of this talk and talk about the significance of this idea.
I'm sorry, just to interrupt again. So it's a very wonderful talk, and I'm enjoying it thoroughly. But the statement, what you call the Wheeler-DeWitt equation, is what I'll call the quantum Einstein equation, but that's just a name.
Okay.
Okay. So the point is that the fact that if states obey, if the bulk states obey the quantum Einstein equation or the Wheeler-DeWitt equation, then holography is automatic. You don't need to impose it. Is a statement that I have made in many talks, and it's probably I've written also some papers on it. So I don't know if you're aware of what we've done earlier, but anyway, it's just
okay. I'm sorry. We should. I perhaps we should talk later, and you can. I'm sorry.
Yeah,
that
maybe.
I was.
Yeah,
thank you. Very much.
I'm very, very delighted for this. It's like a deja vu, Thank you.
Thank you very much. I would like to very much hear more, and perhaps if you could, if you could talk a little bit more, that would be great. Thank you. Apologies for not mentioning that work here. Thank you. Okay. So let me share again. 1 second. Is this still full screen, or because I stopped sharing for a minute? So is this a full screen version right now? Can you see this clearly? This is a black hole.
Yeah. This is fine. Okay. This is fine.
Thank you. Yeah. Okay. Thank you. So now let me point. So what is so I want to speak about black holes, and let me just say what's the cartoon version of what I'm about to say. So the cartoon version is that the statement that information is available outside and states that information about the microstate is always available outside with the right measurements. Now let me point out that this was is often posited as a solution to the information paradox within ADS-CFT, in that if one assumes ADS-CFT, then it's clear there's no paradox because the information is outside. But I emphasize again that here I'm not assuming ADS-CFT. I'm arguing that this is something that follows as a result of the constraints, and therefore the claim is that this understanding of how information is localized in gravity provides a new perspective on black hole information and tells us that there is no loss of information within black holes. One can make this slightly more precise, if one wanted an equation to go along with this. And the equation is that if one looks at the Penrose diagram of an evaporating black hole of this kind, then one can look at this red segment, which is a segment on future null infinity, and define the entropy of that segment. And the entropy of that segment is independent of the upper limit of this segment. And that's the statement that the information outside is neither lost nor gained and stays what it is. So this is the result that one can prove, and you can see that it's rather clear that one could prove it the moment one says that the algebra of observables near the past boundary of future null infinity is complete, because once one has, if one has a set of all observables here, then expanding this segment upwards does not lead to any further gain or loss of information. Okay, now at this point you might say, fine, you're once again, someone might say, here you're saying that the entropy is a constant as a function of the retarded time. But that's not what Hawking found. Hawking found that the entropy should rise monotonically. Hawking found that when the black hole evaporates, the entropy should keep going up and up. And so the question that people ask often is, where is the error in Hawking's argument? You say you have some result that's different, and Hawking says there's some result, and what is the key source of the difference between these two answers? So I now want to explain what that source of difference is. So first, a clarification. Often Hawking's argument of the breakdown of predictability is phrased in terms of Hawking's computation of Hawking radiation. So as we all know, Hawking computed that if one looks at null infinity at the occupancy of photons or other massless particles, one will find a thermal spectrum. And this is good, and this is almost certainly a correct result within effective field theory. Even though we've not observed it, it would be shocking if this was not true for a black hole if we ever got to observe it. But the point is that this calculation is not enough to lead to a paradox. And that is because mixed states are exponentially close to pure states. So if I tell you that I look at the occupancy of photons or I look at the occupancy of gravitons and I find that they're thermal, that doesn't tell me that the state of all the photons or the state of the system is thermal. Now you take the set of all, you take this room, you disentangle it from the universe, it will still be that, any random observable that I measure will look exactly like a thermal observable. In fact, it will look exponentially close to a thermal observable. So Hawking was aware of this. And in fact, if one looks at Hawking's paper, Hawking didn't say this was the reason there was a paradox. In fact, Hawking argued, he provided an argument that's often forgotten in later discussions, which was called the principle of ignorance, to suggest that this computation that he was providing was robust, at least that the conclusion that the state outside was mixed was robust. And let me just detail for you what that argument was. This is actually a screen grab from Hawking's paper, and I'll just read out. So what Hawking said is that one has to introduce a hidden surface about each black hole. And then the principle of ignorance tells us that all field configurations on the hidden surfaces are equally probable, provided they are compatible with the conservation of mass and angular momentum, which can be measured by surface integrals at a distance. This is the statement that the only information one has outside is that which is given by the no-hair theorem, which is a classical statement, and it's false, as I was just explaining, in a theory of quantum gravity as a result of quantum effects. Moreover, then Hawking went on to say that imagine that H1 is the Hilbert space of data on the initial surface, which is Cry minus in our language, H2 be the data on the hidden surface, which one can take to be part of a nice slice inside the horizon, and H3 be the data for the final surface, by which he was thinking of an asymptotic observer. Then he said that, the basic assumption of quantum theory, he said, is that the Hilbert space factorizes, and the asymptotic observer has to trace over this hidden surface, which leads the asymptotic observer to find a mixed state. So Hawking's key argument was actually that the causal structure of the black hole spacetime is such that the asymptotic observer cannot see inside the horizon. And that's true classically, and it's false quantum mechanically. It's, this assumption is the assumption of the split property, which is that there is independent information on the part of the Cauchy slice that's in the interior, which is not accessible to the observer outside. And the previous discussion we had shows that this fails in gravity. So if someone says, where is the error in Hawking's argument? You can point to this paragraph and say, here is the error in Hawking's argument. This is the reason Hawking was led to this result that information is lost. And this is clearly not true. It's demonstrably false in a theory of quantum gravity. Now, let me point out that this result that I'm showing you is also different from the conventional page curve. It's the conventional page curve says that not that the information is outside, but that the information emerges outside according to this tent-shaped page curve. And why is there a difference between that? It is because Page's argument also assumes factorization. If one looks at Page's paper, Page's argument is really for a factorized Hilbert space with two parts, a system of dimension m, another system of dimension n, and then there's a result about the entanglement entropy. This calculation is completely correct, but it applies to non-gravitational systems where the Hilbert space does factorize. In fact, in applying this to black holes, Page explicitly assumed that the black hole subsystem has some dimension n, the radiation subsystem has some dimension m, and these together are factors of the Hilbert space, of which has dimension mn. But since the black hole spacetime does not factorize in this way, there is no reason to expect that the entropy of the radiation should follow a Page curve in a spacetime which is gravitational, as we expect realistic black holes to be in. Okay, I have perhaps 5 minutes more or 5 or 10 minutes more. So let me just conclude by talking about coming to the last part of my talk, which has to do with the comparison with a lot of recent activity on the Page curve. So of course, there has been in the past 2 or 3 years significant activity on computing the Page curve of ADS black holes coupled to a bar. So first, I should say that there is no contradiction between what I'm saying and these computations. And the reason is that these computations are not done in standard theories of gravity. Rather, they're done in theories of gravity where one takes an ADS black hole in this region and then couples it to a bath which is non-gravitational. And therefore, gravity is not dynamical throughout space. It is, you switch off gravity at some point sharply, and beyond that, things are non-gravitational. And what is more, even in the region where gravity is dynamical, it turns out that as a result of a back reaction of the bath, the graviton has a mass, and therefore even in the region where gravity is dynamical, the graviton has a mass, and there is no Gauss law in these models. So these are, even though this is not often realized, these are rather unusual theories of gravity in which a Page curve is expected, as I will now explain. Okay, first let me explain a little bit about the nature of information transfer. So one way to think about this whole setup is, as I said, you think of an ADS black hole. This is the black hole. This is the boundary of ADS. And then you couple it to a non-gravitational bath, which is this pink region. In fact, the computation that is done is a computation of information transfer across some imaginary interface in this non-gravitational region. And therefore, in this non-gravitational region, of course, the Hilbert space factorizes, because that's a non-gravitational region. And so there is a sense in which one can speak of the information inside this dashed line and outside the dashed line. And there is a clear sense in which one does expect to see a Page curve. And so there is no contradiction in the fact in what I said and what one sees in these computations. But there's a little bit more. One can check that if one turns on gravity in the bath, then in this paper with this group of 7, one can check that the Page curve vanishes. So it is not that weak gravity can be approximated by no gravity. Gravity creates a qualitative difference, and even if one has a weakly coupled bath, then there is no Page curve, and so these computations are genuinely non-gravitational. Second, there's a key ingredient of these computations is that it's related to something that was discussed earlier in these talks, the ER equals EPR proposal, which states that if one looks at a part of the non-gravitating bath, this is the same picture as what I showed previously. I'll just say some things in words if this is unfamiliar to some of you. If one looks at a part of the non-gravitating bath that one calls R, that also describes some part of the region in the gravitating region, which is called the island. What is key for us is that this means that the asymptotic geometry of the gravitating region, which is this black region, lacks information about the island. That's available somewhere here. And that's in tension with what I said, where I said if you take a gravitational spacetime, then the asymptotic region contains information about everything inside. How is that consistent with what's happening here? It turns out that these islands cannot work in a theory where the Gauss law applies. And one can show, in fact, as we showed in the second paper with this group of 7, is that if one just takes an island and imagines an island of this kind exists, which is invisible to the asymptotic region in a theory where the Gauss law applies, then such an island would just be inconsistent with perturbation theory, in that if you inserted an excitation, you would be forced to dress it to infinity. And this dressing is something that would be visible in low point correlators. So, if you assume that there was a Hilbert space that was acting here, the action of a unitary operator that should have left correlators here invariant, in fact, changes those correlators. And this is a perturbative problem. It's not some non-perturbative, very subtle effect. It's visible in perturbation theory. And so islands are not consistent in theories with long-range gravity. But that doesn't mean there's anything wrong in the computations of islands that have been performed, because they've all been performed in massive theories of gravity. And one quick way to see why these theories of gravity are massive, for those of you who are familiar with ADS-CFT, is to go back to this picture where one thinks of gravitational region in ADS coupled to a non-gravitational bar. Let me remind you that before coupling this ADS region to the bar, there is a stress tensor on the boundary of ADS that is conserved. But after coupling to the bath, by construction, this stress tensor is not conserved. But in conformal perturbation theory, the conservation of the stress tensor is the statement that the stress tensor lives in a short representation of the conformal algebra. The non-conservation of the stress tensor is a statement that it has picked up an anomalous dimension. And by the standard rules of ADS-CFT, you now have a spin 2 tensor which is picked up an anomalous dimension. And that tells you that in the bath, the ADS graviton has picked in the ADS region, the ADS graviton has picked up a mass. One can see this much more directly by just doing direct bulk computations, as Massimo Porati did. But this is the quickest way to see that in these setups where the bulk graviton is massive. In a theory of massive gravity, there is no Gauss law, and one can see, and as a that just follows. You can see that at the linearized level already. In a linearized theory, the Gauss law appears just from the fact that the metric obeys some constraints. You integrate these constraints, you find the ADM Hamiltonian on the left is equal to, which is what you get by integrating the left side, is equal to the integral of rho on the right side. But in the theory of massive gravity, this constraint that involves the metric is not a total divergence, and so you don't get a boundary integral for the Hamiltonian. So the Hamiltonian is not a boundary term, and the Gauss law does not apply, and neither does this holography of information. Okay, let me just say one last thing, and then I'll stop. I'm almost done. So one way to see this mass is also by thinking of where these computations have been performed in higher dimensions. They're almost always performed in these doubly holographic models that were first explored by Karch and Randall almost 20 years ago. And in these models, this theory of gravity coupled to a bath is realized as a brain world theory inserted in a higher dimensional ADS space. And it's clear, the graviton here is known to be massive, but it's also clear that, in this higher dimensional space, if you insert an excitation in this island region, you can dress it to the higher dimension to this part of the boundary. And the fact that there is this higher dimensional region corresponds to the fact that when you reduce the theory to the brain world theory, you get a mass in the lower dimensional effective description. Okay, great. So let me just summarize and I'll stop. The point of this talk was that standard theories of gravity store quantum information very differently from local quantum field theories. One can give some non-perturbative algebraic arguments for this, but also very explicit perturbative analysis of the gravitational constraints which lead to this result. This sheds light on why gravitational theories are holographic. What is the reason that gravitational theories are holographic and non-gravitational theories are not? But accounting for this unusual localization of information also helps to resolve several paradoxes about black holes and identify the precise error in Hawking's argument for information loss. Theories which have islands do not obey this principle of holography of information. And islands are inconsistent in standard theories of gravity with the Gauss law, but they are consistent in specific theories of gravity where the graviton is massive, which is indeed where these computations have been done. Okay, so thank you for your attention, and I'll stop here.
Thank you very much, Subra, for a very nice talk. And it's time for questions.
Again,
can I? Sorry. Go ahead.
Yeah, go ahead, Sumati. I've already asked a couple of questions.
Okay.
So you please go ahead.
Yeah. So just one comment about if we think of entanglement measures and so on. If I consider, if I think of it from a space-time point of view, because you're talking about, you know, the information on a hypersurface, and that the entire information, if you think about it in terms of the wave function, that the entire information is in fact contained in this holographic sense. If I just take quantum field theory, more the algebraic formulation, and I have regions which are causal complements of each other, which is the case with the two, you know, in the Kruskal extension of the left and the right parts of Churchill. They're causal complements of each other. Then the full algebra, this is just in quantum field theory. I'm not even invoking quantum gravity, which you're talking about. We know that there is an entanglement between these two wedges, and that the algebras that we have on the left and right, in this case, they're isomorphic to each other because the regions are isomorphic to each other. But in general, this is not something that is required. And so, to me, the fact that we have entanglement, which means that you have a reduced density matrix, however you define it, in the space-time sense, in an accurate, you know, in a more appropriate space-time sense, suggests to me that what you have is something that must be fundamentally non-unitary in one part. So where does that way of thinking about it? I mean, you're making assumptions about quantum gravity, which you know, so I'm not sure whether, if we even think about algebraic quantum field theory from a space-time point of view rather than states at a given time, then this isn't even commensurate even from that point of view.
Can I answer? I understood the question. So I think that in algebraic quantum field theory, when you think of causal complements, you get two commuting subalgebras. So the fundamental assumption of algebraic quantum field theory is that if you take a region and its complement, you get a commuting subalgebra. The point of what I said was that such commuting operators do not exist in a theory of gravity if you take a region to be a bounded region and its complement to extend out to infinity. So in the case of the Kruskal extension, you do have such commuting algebras even in gravity, and it is indeed true that the evolution of one part would be non-unitary because the extension, both the parts, both the left and the right go off to infinity. They have an asymptotic part associated with them. The geometry that one is speaking about when one speaks about a single-sided black hole is that one thinks of a Cauchy slice. On that, one has what you would call a causal diamond, and the complement of that is the complement of the diamond. So I don't know how to draw in Google Meet, but you know, you basically, you have a region here, a ball, and then the complement of the ball. In algebraic quantum field theory, a fundamental assumption is that those operators are commuting operators. So there is entanglement between them in the vacuum, and you know, there's even a Bisonano-Wichmann construction of, you know, how you can use some Tomita-Takisaki theory to try and construct an isomorphism between them. But the fundamental point of what I said is that those commuting set of operators do not exist, in that if you try to write down an operator in the interior of the ball, then that operator does not commute with operators outside. And one can see this explicitly.
Is this, sorry, is this with the assumption? So no. I don't understand, what are the assumptions that you make about the theory of quantum gravity?
This is not an assumption. So starting with perturbative gravity, one can show that this is true in a theory of perturbative gravity. One can also show non-perturbatively in the precise assumptions that one makes there. I can detail and I can tell you in more detail. So the first thing is, that was the reason for the Wheeler-de Wit perspective. If one just starts with perturbative gravity, one can see perturbatively already that there are no commuting observable. So there is no sense in which you can define an operator in the interior that commutes with things outside. Let me give you a very simple example of this in perturbation theory. Imagine that we are in let's be in ADS to avoid infrared issues. And in ADS, there's a unique vacuum. So just think of measuring the Hamiltonian outside. So in the vacuum, in a quantum field theory, in algebraic quantum field theory, you would have these entangled states and a lot of information about the interior of a ball that was missing if you looked only at the exterior. But in a theory of gravity, let's just measure the Hamiltonian, which is the degree of freedom outside. It's given by the ADM Hamiltonian near the boundary. The moment you measure this and you find it zero, even that its expectation value is zero, you know everything about the state in the full Cauchy slice, including the interior. So you see in this one example that just measuring 1 degree of freedom outside has fixed for you everything in the interior. The only way you could break this is by breaking the fact that the Hamiltonian is a boundary term, which would require you to break diffeomorphism invariance. So in perturbation theory, it's already clear that these commuting operators cannot exist, because if they did exist, you would be able to find a unitary operator acting in the interior of the ball that commuted with the Hamiltonian. So this is a perturbative statement. And if one assumes that, diffeomorphism invariance persists in the non-perturbative theory and the Hamiltonian is positive, then one can extend this to a non-perturbative statement, in that you can never find a unitary operator. But already in perturbation theory, I think it's clear from this example that I gave that these commuting sets do not exist.
Just to follow up, so are you also saying then that these, and I think that's what you said, is that these thermals, that the state cannot therefore be thermal and so on and so forth. So it's actually, and that's a statement about perturbative quantum gravity. Is that the statement that you're making? Okay. All right. Yes. I mean, again, we don't know what that theory is, but all right, I'll take it.
Perturbative gravity, we do know, right? We just measure the Hamiltonian outside, it's a pure state. There's no, if let's say the whole state was in the vacuum, then, in a quantum field theory, you measure all operators outside, you would not have information about the interior, you would get a mixed state.
But it's a sick theory. I mean, perturbative quantum gravity, unless you've got, tell me exactly that it's an effective theory and so on and so forth, and unless you tell me how you have any sense in which you renormalize the theory. So all I'm saying is that under what assumption, there must be assumptions in that theory that you're putting in. So when you say
I'll tell you the
theory of quantum gravity, I have a problem with that.
I'll tell you the assumption I'm putting in is that the Hamiltonian is a boundary term, which is the statement diffeomorphism invariance is preserved. And the reason this is I don't have to worry about the non-renormalizability is because this is a low energy effect. I'm just checking that H is equal to 0 on the vacuum. I mean, that's almost the first renormalization condition you would put, that the boundary integral of H is 0 on the vacuum. So that's not sensitive to how what you do, what counter terms you add to the theory. And
right.
Yeah.
Sorry, as I said, it's an excellent talk, and I just want to commend you first for this talk. Second thing I want to ask you is, or sort of share my understanding, is that basically in sort of a layman's language, you could say that Hawking as well as Page ignored the quantum gravitational degrees of freedom. See, their calculation is mostly done with a space-time which may be dynamical, but which is certainly classical. And unless you include the quantum degrees of freedom, see, it's like in excluding photons in an atomic physical experiment. I mean, you will certainly lose the unitarity, right? But it's more than that, because in gravity, you not only have the gravitons, you also have the strings, the Wilson lines of gravity in the non-perturbative picture. So there's a lot more in quantum gravity. And if you take all these things into account, and of course, the assumptions you made about a positive Hamiltonian and all that, with the Einstein, the quantum Einstein equation in force, I think everything goes through. So I don't see any loss of unitarity in that sense if you take the whole Hilbert space into account. Would you agree?
Yes, I agree. That in these calculations, the effects of quantum gravity were ignored. It was generally believed that we do quantum field theory as an effective about curved space-time, and we ignore gravity. It was generally believed that this will give you corrections which are accurate. You can keep working with this order by order in perturbation theory, but there's an effect that starts appearing already at leading order in perturbation theory and becomes more and more significant. And that effect is the fact that you have this unusual localization of information. So that effect was ignored in these computations.
Absolutely.
In the end, to get information from outside the black hole, you need to make measurements at order e to the minus s. That's just a basic prediction of statistical mechanics. And there's no claim that in perturbation theory you get information from outside immediately, but this effect is already visible in perturbation theory. And because it's such an unusual effect, it was ignored and has been ignored in many computations. I agree with that.
Yes, that's excellent, because I think I have it written somewhere in some papers. I'll certainly send them to you, Subrat.
Okay,
very
thank
nice.
you. Thank you. Yes, thank you very much.
Subrat, just a small question, nice question maybe. First of all, I thank you for your wonderful talk. It's a very nice talk. So just I wanted to understand one of your statements. You mentioned that for a distant observer, it's not possible for him to see inside the horizon classically, but quantum mechanically he can see inside the horizon. So if he sees, if this is possible quantum mechanically to see inside the horizon for the distant observer, then it would actually mean that he is all the way, he can see up to the singularity. So in some sense, it is no more a black hole. If I have understood correctly, it is like a naked singularity. And so what does it really mean to see inside the horizon quantum mechanically? I can understand that quantum mechanically something can, classically a black hole cannot radiate, but quantum mechanically it can radiate. That I can understand. But what does it mean to see inside the horizon quantum?
Indeed, thank you. So so as you said correctly, the cause, if you take seriously, these effects, then one cannot take seriously also the causal structure of space-time. So the causal structure of space-time that one thinks about is a good thing to do classically. It's a good thing to do within quantum field theory, where gravity is switched off, and one can in fact see that these effects that I'm speaking of all come with a factor of h bar g. So if you take either g to 0 or take h bar to 0, these effects go away, and there's a perfectly good sense in which information is localized in the standard way. And indeed, the notion of a horizon is a classical notion which ceases to make sense in quantum mechanics. One can, in a black hole, there is still, you can hide information about the microstate all the way up to non-perturbative accuracy, but in the end, one cannot really speak of a notion of a horizon in the quantum theory. Let me just point out, however, that on the Cauchy slice, the singularity is not there. So, it's not that if one sees into the horizon, one sees the singularity at the center. So everything I said was happening on a Cauchy slice. If you were to draw a Cauchy slice in a black hole spacetime, there would be no singularity. It's what you would call a nice slice. So you would see some state on a nice slice, and so it's not that that's just a minor comment. It's not that one sees inside and there's a naked singularity. There's just a Cauchy slice, and one has to be careful about the way in which information is localized. And of course, there is interesting physics that comes about when the matter collapses. So even if one thinks of evolution on nice slices, in the end, there is a region of space-time in which there is strongly coupled physics, and one has to understand that. And I'm not saying I have nothing to say about that in this talk. So that is indeed something that remains. But you're right, absolutely, that the notion of a horizon is a classical notion, which I think one shouldn't take too seriously. It's a very useful notion. I mean, but one shouldn't take it seriously if one starts asking in principle questions of the kind that Hawking was asking.
Also, one more, just Freddy, do you think that this Hawking's argument, you mentioned very nicely why Hawking's arguments are a little bit erroneous, but is it true that the Hawking's calculation also, the arguments also fail because it's an Euclidean calculation?
No, Hawking's computation of Hawking radiation is perfectly fine. That's an effective field theory computation. And I think there is, at least, I don't see how that could be wrong unless our basic understanding of field theory or gravity is wrong. So the computation of Hawking radiation is not at all erroneous. But as I tried to emphasize, the argument for information loss doesn't come from radiation. It comes from the argument that the radiation is exactly thermal all the way up to exponentially small effects. So, if one has thermal radiation, that is fine, and that is consistent with unitarity, because if you just had exponentially small terms in that radiation, those would be enough to preserve information. So the argument that Hawking gave really was relying on the idea that the causal structure that you get is exact. There's a causal structure that you get from the classical geometry, and that is exact. So it was not that, we compute some 2-point function of photon occupancy, and that tells us the state is thermal. That is far from precise enough to tell us that the state is thermal. And there is no computation of this kind. But the argument relied on the causal structure, which I'm claiming one should be much more careful about in a quantum theory of gravity.
Thanks a lot. Thank you very much for that. Thank the speaker. There are 2 more questions. I'm sorry.
Sure, yes. Of course, yeah.
Ghulam, please go ahead.
Okay, thanks, Subrat. So I have a rather naive question. I mean, the property that Wheeler-DeWitt equation or the Hamiltonian for the gravitation is 0. It's there in the classical theory, right? It's a property of the classical theory.
Yes.
Right?
Yes.
So what is the role of quantum gravity is there? I mean, the statement can be made at the classical theory level.
Yes.
The reason I'm asking, let me say the other side of the picture. Let's say I consider the boundary volume problem that we study in our undergraduate courses, right? Electrostatics. I fix the boundary field at the boundary, subject to Gauss constraints equations are right, my bulk electric fields are potentials are fixed. Will that should I call that also an holographic example?
Of course not. Of course not. Electrodynamics is not holographic. So the answer to this is the following. So imagine solving the classical equations of motion. You're right. In the end, the Wheeler-DeWitt equation you can think of as just d00 equal to t00, right? And classically, you have a Birkhoff's theorem, which tells you I can think of various kinds of t00 in the bulk, maybe a dilute gas or a more compact gas. And by Birkhoff's theorem, the metric outside is exactly the same. It only cares about the integral of t00. Okay? But notice that now in the quantum theory, that's not how things work. In the quantum theory, what you need to do is you need to look at the way you would work, the way we wrote down solutions, is you think of an eigenstate of the energy of the matter, entangle it with an eigenstate of the metric. Right? So if you look at the fluctuations of G00 at infinity, those fluctuations which make no sense in the quantum theory, right? The fluctuation of h squared, expectation of h squared is expectation of h the whole square.
So maybe let me rephrase the question. What information are you talking about? Information of what kind? Is it classical in nature or like purely quantum mechanical?
Yes, it's purely quantum mechanical. So if you look at expectation of h squared, okay, think of just Birkhoff's theorem, which is where the classical quantum discrepancy becomes very sharp. So think of a dilute gas and a gas which is a compact gas. Spherically symmetric. So in the classical theory, you would solve the equation. You would find in both cases the metric outside looked like 1 minus m over r. But m was the total mass. It would be the same for the dilute gas, and it would be the same for the compact gas. Is that right?
Correct.
Now let's look at expectation of h squared. H being the ADM Hamiltonian. This expectation of h squared. In the classical theory, this is the same as expectation of h the whole square, because in the classical theory, there's no there's no sense in which there's any fluctuation in this. Notice that expectation of h squared differs between the compact gas and the dilute gas, because the compact gas, by virtue of being compact, has a larger superposition of energy eigenstates, whereas the dilute gas can be made with a smaller superposition of energy eigenstates. So you see already how looking at the fluctuations of the Hamiltonian in the quantum theory gives you more information than you have in the classical theory. And fundamentally, the point is that to localize, there's no such thing as a localized energy eigenstate in the quantum theory just by virtue of the uncertainty principle. And therefore, if you write down solutions to the equation, to the Wheeler-DeWitt equation in the quantum theory, every time you have an energy eigenstate in the bulk, you entangle it with the degree of freedom of the metric at the boundary. And therefore, quantum correlators of the metric and of degrees of freedom, contain information about the state in the bulk. There is no analogous classical effect. Okay? I'll say it one more way just to make it totally clear. If you think of, let's say you said, I can change the state in the bulk in some way so as to not change anything at infinity. Okay? So
that I cannot do even classically, right? If you solve it, if you solve for classical general relativity, you have to ensure the constrained surface are maintained. Of course,
you can change the state in the bulk where it's Birkhoff's theorem. The example I was giving right now, dilute gas and compact gas, you just reorient the matter in the bulk while keeping it spherically symmetric. You keep everything at infinity completely unchanged. Right? So you just change the density of matter in the bulk. All you see at infinity is the total mass. You don't see the distribution of the mass. So classically, you can do it. Now, quantum mechanically, if you wanted to do it, you would have to make a perturbation that was zero energy. Right? But if it was zero energy, the operator that does it would be delocalized, so it would fail to commute with some operator at infinity. On the other hand, if you try to make a localized operator to perform this operation, it would be non-zero energy by the uncertainty principle, and therefore it would fail to commute with something at infinity. So these are several ways in which you can understand the difference between the classical and the quantum.
So I'm not completely convinced, but because we don't know the quantum theory of gravity.
No, this is not. I don't think that's a good argument, because these are very robust arguments that are based on the low energy theory.
No, I'm saying that what is not there in the classical theory itself that we have in the quantum theory. So my question is rather, because you see, when you have a constraint, right, it is not all degrees of freedoms are actually there. I mean, in the sense that when you impose the constraint, certain relations are automatically fixed. So in the sense that certain...
I can explain more, but I just explained the specific difference why in Birkhoff's theorem and the classical theory, you could hide information by distributing the density of matter differently, and how you can't do that in the quantum theory. As that's the example I gave. So that's it's very clear. You can see the difference between the classical and the quantum theory. In electrodynamics, of course, by the way, it's not holographic. You can just think of trace of
No, that was just trying to give the other side of the picture. That
no, there's no other side. There's no uncertainty principle for charge.
Okay, I'm done. Thanks, Subrat. So I think we can still talk, but I got the basic idea is clear what you're trying to say.
Yeah.
At least I can have quantum states which are having similar kind of classical behavior, but internally could be different. Or if you get the information at the boundary to be frozen, that will freeze even the wave function. So.
Yeah. And maybe Amitabh has a question.
Yeah, Subrat. So my question is along the line of what Sumati was asking. Like in the first part of the talk, I wanted to know where the small correction theorem has gone wrong. Samir Mathur's correction theorem.
Small correction theorem assumes precisely the same. I didn't mention this this argument about strong subadditivity. That argument was based on strong subadditivity, which assumes precisely the factorization of the Hilbert space. It assumes that the Hilbert space factorizes into HA times HB. You know, you take a nice slice and you factorize the Hilbert space into 3 parts. And so the argument for fuzzballs or the argument for firewalls was also based on factorization. I didn't keep that slide for lack of time, but it's precise. Once again, you know, the idea that you have exact locality, which goes into the small correction theorem. I mean, small correction theorem is based on strong subadditivity, which is just not true if the Hilbert space doesn't factorize.
But there must be a parameter range where your effects are small. The effects that you are talking about, they are small. And in those contexts, the small correction theorem should apply.
No, there's no such parameter range for black holes for the following reason. You see, you could say that, let's say I have a piece of coal which evaporates, right? And for that, I expect to see a page curve. I mean, because for a piece of coal, clearly if I want to see a piece of paper burning, you shouldn't be talking about quantum gravity effects. The reason for that is to see a page curve, you need to keep track of effects of size e to the minus s. But s for ordinary systems has nothing to do with G Newton. You know, in our world, s for most ordinary systems is much smaller than energy scale over Planck scale. So therefore, for most ordinary systems, the effect of seeing the entropy, or seeing the purity of the state, which has to do with making measurements at size e to the minus s, is something you can do while ignoring the effects I'm talking about, which are all controlled by energy scale over Planck scale. However, for the black hole, energy scale, which is the Hawking scale, energy scale, over Planck scale is 1 over s. I mean, sorry, it is s. Okay? So there is no separation of parameters. So if you try to see whether the state is pure, by making accurate enough measurements, you're forced to also contend with the non-local effects that I'm talking about. Whereas for ordinary systems, you can separate those effects. So it's not a good argument to say that for ordinary systems, you don't have to bother about these effects, because for ordinary systems, there's a parameter which allows you to define the entropy without worrying about the effects I'm talking about, which is simply the separation between S and E over M Planck. Whereas for black holes, there is no such separation because these two parameters are linked. So you try and take, even in the landscape, there's no such separation. You try and take G Newton to 0 and the entropy of the black hole goes to infinity. And so if you want to see the page curve or see the fact that the state is pure, you have to also contend with the fact that these effects exist in gravity.
Okay, so I think let us stop here and let us thank Subrat once again for a very nice talk. Thank you very much, Subrat.
Thank you.
Tea time, we shall not have the tea time probably, because it starts from the next session starts from 4:40. It's already 4:42. The next session will be chaired by
session. Sundan,
yes.
Could you please postpone the session by 15 minutes so that people can have tea?
Okay, that session can. So the next session will start at maybe we can meet at 4:50, because otherwise the other two speakers, or maybe 4:55. Okay.
4:55. Yeah.
Yeah. 4:55. 4:55 would be. So the next session starts from 4:55, and it will be chaired by Professor Amitabh Lahiri. You just need to edit the time. 4:55 over. আর আশিস নেক্সট স্পিকার হচ্ছে আশিস, একবার দেখুন আশিসের স্লাইডে।
Ashish, are you there?
Sir, can you share your screen?
Ashish,
Okay.
can you check if the sharing is working? Good. Okay. It's working. Okay, so let's start. Okay, so welcome back after the tea break for the post-tea session of the second day. This is a slightly long session because we have two speakers from diametrically other side of the world, and those two will be in their early morning. So they are at the end of the session today. Today we have two short talks, 20-minute talks contributed, and two long invited talks after that. The first speaker is Ashish Saha from Kalyani University, and he will be speaking on mutual information, islands in black holes, and the page curve. Ashish, please.
Thank you. So I would like to thank the organizers for giving me this opportunity. So the title of my talk is Mutual Information, Islands in Black Holes and the Page Curve, and it is based upon this work. So this is the outline of my talk. So firstly, we shall see how to understand the Hawking's paradox in terms of the page curve. And we then move on to consider a specific gravitational model in order to compute things in detail. We then compute the fine-grained entropy of the Hawking radiation and see how does the island influence this kind of calculations. And then we move on to compute the mutual information of subsystems and see that this saturation of this mutual information leads to the correct page curve. And after computing the fine-grained entropy of Hawking radiation with the help of saturation of mutual information, we revisit the condition associated with the vanishing mutual information. And we then compute the page time. And lastly, we see some extensions and some feature directions. Okay, so Hawking's original observation was that the entanglement entropy of radiation outside the black hole is monotonically increasing. However, this statement leads to a paradoxical situation, and one can take the help of the page curve to point this out. So the page curve basically portrays the time evolution of the entanglement entropy. So if we consider the total system to be the black hole and the radiation, and the state of the full system is a pure state, then S of R, which is the fine-grained entropy of the radiation, will be equal to the S of R complement, which is the fine-grained entropy of the black hole subsystem. Now, the fine-grained entropy of the black hole subsystem is bounded by the coarse-grained entropy of the black hole, which is basically the Wittgenstein-Hawking entropy. So, as S of R and S of R complement are equal, and S of R complement is bounded by SVH, so S of R also will be less equal than the SVH. So by fine-grained entropy, I am following the basically trying to mean the von Neumann definition of entropy, and the coarse-grained entropy, in the simple sense, can be represented as the entropy which satisfy a specific set of thermodynamic laws. So now this S of R being less equal than the SVH is in contradiction with the Hawking's observation of monotonically increasing entanglement entropy. So we can take the help of some schematic diagrams and point this out. So in this case, in this one's for the eternal black hole and this one's for the evaporating black hole. So the green curves represent the coarse-grained entropy of the black hole. If we consider a two-sided eternal black hole, so this is basically the 2SBH. So we can see that up to a certain time scale, this red curve, which is basically the fine-grained entropy of radiation, increases and or basically satisfy the property SR being less equal than SBH. But however, once we cross this certain time scale, the S of R doesn't hold this property and leads to a paradoxical situation. So same scenario happens for the evaporating black hole also. So this certain time scale which we are talking about, at which the S of R, that is a fine-grained entropy, is equal to the coarse-grained entropy of the black hole, is known as the page time. So the post-page time scenario basically resists the paradox. So now we consider a specific gravitational model. So in this case, we start by considering an eternal two-sided BTZ black hole, which can be characterized by this metric, where L is the ADS radius and R plus is the position of the event horizon. Now, the ADS boundaries, it has been noted that have a intrinsic reflecting nature from the point of view of Hawking quanta. So the Hawking quantas bounce back from the ADS radius, and the black hole is basically in equilibrium with its own radiation. So in order to capture these Hawking quantas, we now follow the standard technique of gluing non-gravitational flat spacetime, also known as the auxiliary thermal baths, on both sides of the two-sided eternal black hole. And this basically introduces or imposes absorbing boundary conditions for the Hawking quanta. So this is the basic conformal diagram for the setup. So these vertical lines are being the ADS boundaries, and these triangular portions are the flat auxiliary thermal baths, and inside this portion is the BTZ spacetime. So in the Kluge-Skull coordinates, we can write down the BTZ geometry as like this, where the omega is represented in the following manner. We assume that the whole system, that is the non-gravitational thermal baths and the BTZ spacetime, is filled with conformal matter of central charge C, and the S wave part of the matter only contributes. So we are considering only the massless modes. Now, the fine-grained entropy of the Hawking radiation is identified by the von Neumann entropy of quantum fields on the region R. So these are the region for collecting the Hawking radiations in the exterior. So as you can see, there are two regions in the left and right. So the R plus being in the right exterior, and R minus is in the left exterior. So these regions, they extend from the boundaries B plus minus to the spatial infinity, and the position of this B plus minus are being TBB and minus TB plus I beta by 2 comma B. But the imaginary part basically represents that the B minus is in the left exterior of the horizon. Now, as we have mentioned, that considering the state on the full Cauchy slice, if we consider the full Cauchy slice is a pure state, so S of R again satisfy the following property of being equal to the S of R complement. Now, once we have the S wave approximation and keeping in mind the S of R being equal to the S of R complement, the matter field theory reduces to the effective 2D CFT, and we can write down the finite part of the S of R as C by 3 log of D, where this D is the gravitational input, which we can substitute from the BTZ metric. And once we have substituted this from the bit symmetric, we get the following expression. And now if we consider the late time scenario when TB is much greater than the beta, the above expression shows that it is linearly time independent, but TB represents the time. So there will be a certain time, or after a sufficient amount of time, it will be much greater than the Kurzgesellschaft entropy of the black hole. Now, this inclusion of these auxiliary domains known as the islands in the interior of the black hole leads to the correct page curve. So the after the page time, this island basically dominate, or the saddle points, which we should mention earlier. So the on the a simple point on the origin of these islands can be interpreted in the following: that the application of replica method to compute the von Neumann entropy of matter fields in the region R so leads to a partition function as a gravitational path integral on this replicated geometry. So one is to compute that Zn. So one of the saddle points of this path integral is known as the replica wormholes with correct boundary conditions, and which basically connects different copies of the system, which we usually consider in the replica method. So this mouth of the replica wormholes eventually led to the island formula, and one can say that up to the page time, the other saddle point, that is known as the Hawking saddle point, dominates and gives the monotonically increasing entanglement entropy of radiation. And after that, the island, or more precisely the replica wormholes, dominate. So this leads to the following island formula. So one can see that there are two parts in the formula. That is, the first is the geometrical part, that is the calculating the area of the endpoints of the island, denoted as the delta I, which is known as the quantum extremal surfaces, divided by 4gn, plus the matter part, or more precisely the matter von Neumann entropy, the matter fields on the I union R region. And after computing the quantity in the curly bracket, one needs to extremize the I parameters, and if there are more than one extremal values, then one with the minimum has to be chosen. So this can be represented in the following fashion. So this is the region I inside the interior, and these are the endpoints A plus minus with the coordinates TA and minus TA plus I beta by 2 comma I. And again, one thing is that we can also again use the fact that the matter entropy in S matter I union R satisfies S matter B plus union B minus, because the full state on the full Cauchy slice is the pure state. So this can be evaluated by computing this von Neumann entropy corresponding to disjoint interval B plus and B minus. So that can be done by incorporating this formula, where again these D's are the gravitational input, which will be substituting from the BT symmetry. So at late times, the above expression of S matter B plus union B minus can be simplified in the following fashion, where one sees that the leading terms are nothing but the S matter on the B plus and S matter of B minus, and these are the terms of the order of e to the power minus t by beta. So if we drop down this kind of terms or suppress these terms, so the island formula under the late time approximation can be simplified in the following fashion. Now, as we are working with the BTC geometry, so that the area part will be twice of 2 pi a by 4gn. 2 arises due to the two endpoints of the island. And once we follow the standard extremization policy in this scenario, that leads to Ta minus Tb is approximately equal to 0, because we have dropped down this kind of terms, and A is nearly equal to R plus. So once we have obtained this, we can substitute in this equation, and we see that the S of R is nothing but the 2SPH as the leading term. Now, taking clue from this late time approximation, and we note that that equation can be rearranged in a familiar form. So we see that that equation can be rearranged into in order to recast the mutual information between B plus and B minus. So we come up with a proposal that just after the page time, inclusion of the island contribution leads to the exact saturation of the mutual correlation between B plus and B minus. That is, I of B plus and B minus will be 0, and see that what kind of things arises under this condition. So we observe that this I, if we demand to be vanish this I, so vanishes only if the following condition is satisfied, that is Ta minus Tb is equal to R star A minus R star B, where R star the tortoise coordinate, which is like this. So it relates the time differences and the spatial differences written down in the tortoise coordinate. So one thing this equation enables us that we can write down the Ta in terms of the Tb, R star and Rb. So once we have obtained this Ta, we can substitute this Ta into the S matter of B plus union B minus. So once we substitute all the things we need, we get that the S matter of B plus union B minus, which is also the S matter of I union R, is nothing but this equation. So it is interesting to observe that the obtained expression of S matter I union R has no time dependency at all. So this Ta, this value of Ta can be interpreted as one of the extremized value of Ta, which we have obtained from the by demanding the vanishing of mutual information between B plus and B minus regions. Now again we put down the area terms, that is area of delta I divided by 4gm. Again, that is basically the similar, so 2 into 2 pi a by 4gm. Now one thing that is still needed to be found out, that we need to find out the A. So in order to find out A, we follow the extremization condition and find out that A is like this, where it can basically represents that the QS, or the quantum extremal surfaces, has just formed outside the horizon of the BTZ black hole. So the region I almost entirely covers the whole interior on the Fourier slice. So once we have computed this A, we can substitute this A in the expression and find out the S of R is the following, where the leading piece, again, the 2 SBH, and these are the subleading corrections. So also one can say that the expression of S of R contains universal corrections involving the Hawking entropy of the black hole. So up to this point, we can say that the saturation of the mutual information, that is I of B plus and B minus, leads to the correct page curve, because it has removed the time dependency, and also it is equal to the leading piece is nothing but the 2 SBH, which is basically the coarse-grained entropy of the black hole subsystem. Now we can revisit the condition which we have obtained, that is this condition. So we have computed the exact expression, or more precisely the extremized expression for A, and if we just substitute that expression in the condition of vanishing mutual information, we obtain this Ta minus Tb expression, which is before, as we should have mentioned that before, once we have dropped down this kind of terms, this was basically 0. Now you can see that this is not 0, and the leading term is found to be nothing but scrambling time. So the scrambling time has the following, the formal definition as the minimum time required to retrieve the information just after sending the information into the black hole, just after the page time. So as soon as the time difference Ta minus Tb after page time equals the scrambling time, the mutual information between B plus and B minus vanishes, and which results in a time independent form of the S of R. So 5 minutes. Okay. So the page time, now the page time can be defined in the following manner, that the fine-grained entropy of radiation stops growing at a particular time scale, which we have pointed out earlier from the schematic diagrams. So we have two expressions of S of R. Once we have computed from the which have shown us that it is linearly time dependent, and another one which we have computed from this. So we can equate these two expression at that Tb is equal to Tp. So this leads to the following expression, where the leading time is the familiar page time, and these are the subleading corrections. To summarize, the inclusion of the iron contribution leads to the saturation of mutual information between B plus and B minus, and this happens due to the reasons that the following, the time difference between Ta minus Tb equals the scrambling time. And this vanishing of I yields a time-independent expression of S of R, and eventually leads to the correct page curve. Also, another thing is that the S of R contains universal corrections, which are logarithmic and inverse power law in form. Now we observe this vanishing of mutual information condition for another gravitational model, that is for asymptotically flat eternal Schwarzschild black hole in 3+1 dimension filled with a conformal matter of central charge C. So we observe that again this vanishing of mutual information only satisfied if this condition is satisfied, that is Ta minus Tb has to be equal to the T scrambling, and there will be some correction terms of 1 by SBH order. And the fine grained entropy of Hawking radiation is found out to be like this. Again, the leading piece being the 2 SBH, and the subleading corrections are of logarithmic and power line form. So some future direction in this context will be observing the saturation of mutual information in the doubly holographic setup. That is very interesting in this context, and one can also include alternative or modified gravitational theories in this context. Thank you.
Thank you, Ashish. And it's now time for questions. So, anybody who has any questions, please put up a hand. Any questions? Okay, so if there are no questions, let's go on to the next speaker. And our next speaker is Sunandan Gangopadhyay from the Central National Center. He happens to be the main organizer of this conference, and he will be speaking on Bianchi 1 cosmology. Let's see. Cosmology of Bianchi type 1 metric using renormalization group approach for quantum gravity. Sunandan, thank you.
Okay, so I hope you can hear me. I'm audible. So, as mentioned, the title of my talk is Cosmology of Bianchi type 1 metric using denormalization group approach for quantum gravity. And this is the first talk that is being given from the beginning side. So, and this work was done in collaboration with my student, Deepika Mondal and Professor Amitabh Lahiri of the center. So it's published in this paper. So first of all, I would like to mention the plan of my talk. So first of all, I shall be talking about the denormalization group approach, quantum gravity, what this approach is in the first place. And then I shall briefly discuss the exact denormalization equation, and then shall come the model that I want to study, Bianchi type 1 cosmological model with running impulse constant and cosmological constant. And we shall discuss this model in the presence of two methods, kinds of matter. One is radiation and one is stiff matter. And then I shall try to summarize my results. So this is basically the plan of my talk. So let me tell you what is the renormalization group approach to quantum gravity. So all of us know, it is quite familiar to all of us, that the consistent quantization of general relativity, 4 dimensions, is the holy grail of theoretical physics. And the traditional approach to quantum gravity, so far there has been many approaches. For example, string theory claims to be one of the approaches, one of the theories of quantum gravity. Good quantum gravity is there, non-commutative geometry is there. But traditional approach to quantum gravity is as follows: one treats the Einstein-Hilbert action. This Einstein-Hilbert action is regarded as a fundamental action, which should be quantized along the same lines as the familiar denormalizable quantum field theories. For example, quantum electrodynamics and Yang-Mills theories, non-abelian case theories, which are denormalizable. One expects that to quantize Einstein-Clifford action in the same lines. But the problem is that quadratic treatment of general relativity is quite difficult, both technically and conceptually, because it is not renormalizable. And therefore, this non-renormalizability of GR hampers a meaningful quadratic analysis. However, one can argue, as was also being mentioned in Sugar's talk, some comments, one can argue that gravity should not be quantized at all, because Einstein gravity is an effective theory. An effective theory, we know, does not need renormalization at all. And it is an effective theory which results from quantizing some yet unknown fundamental theory, that the theory that we do not know, and the candidates for these theories are string theory and quantum gravity and things like that. But from in the 90s, so it's 3 decades almost now, a new field theoretical approach to quantum gravity based on this view has become popular, and this is the functional denormalization approach, group approach to quantum field theory itself. But this functional denormalization group approach is now being applied to understand gravity. So this is the brief beginning of my talk. So let me just briefly tell you what is the functional group renormalization group approach. In this approach, this has nothing to do with gravity, and it is a purely quantum field theoretic approach. In this approach, the low energy effective action is obtained by solving the exact functional renormalization group flow equation in terms of the momentum scale parameter k. So let me explain what do I mean by that. What I mean is the following. One tries to obtain a differential equation, a RG flow equation for the low energy effective action, and that effective action is valued at some momentum scale k. And when one solves this differential equation for this effective action, it results in the running of the coupling constants in the theory. The theory that comes from this formulation has its bare action corresponding to a non-trivial fixed point of the RG flow. The existence of a UV fixed point also indicates that the theory is asymptotically safe, and this asymptotic safety idea was first put forward by Weinberg, who is one of the founding figures of quantum field theory, and he passed away last year. Other figures of quantum field theory, and it was his idea that there may be a UV fixed point, and the existence of such fixed points actually mean that the theory is asymptotically safe. So based on this idea, the renormalization with this idea of the functional renormalization group approach to quantum field theory, this is now being applied to gravity. The RG approach regards Einstein gravity to be valid near a certain non-zero momentum scale k. This means that the Einstein gravity arises from some fundamental theory by a partial quantization, quote unquote partial quantization, in which only excitations with momentum larger than k are integrated out. Here, one should mention with a word of caution, by integrating out, I mean that you include the momentum modes larger than k. They are not being thrown away. And while those with momentum smaller than k are not included at all. A formulation of asymptotically safe gravity based on an Euclidean effective action is used. It is defined such that it correctly describes all gravitational phenomena, taking into account the effect of all groups at a momentum scale k. There is one more ingredient in this formulation. The effective average action is based on a modified theory. This action includes, in addition to the bare action of the theory, a regulator term which suppresses all the infrared modes with momenta below the chosen cutoff k. So that is what I mean by momenta with smaller than k are not included. And how do you do that? You do it with the help of a regulator function. So this is an important ingredient. So let us just briefly review the formalism of general quantum field theory, which all of us are familiar with. In quantum field theory, in the path integral approach, we start by writing down the generating functional of Euclidean correlation functions, which is Zj, and this gives you all kinds of Green's functions, connected and disconnected both. And from here, you can construct the Schwinger functional, which is logarithm of Zj, and this Schwinger functional gives you only the connected to this function. And from the Schwinger functional, the effective action is obtained by a Legendre transform. And this is the effective action that you have, which can be constructed from the Schwinger functional. This is standard quantum field theory, which we are all familiar with. Now one replaces all these quantities by scale-dependent quantities. So you write down the scale-dependent generating functional, and what the important thing is this term here, which is the regulator term. From the scale-dependent generating functional, one writes down the scale-dependent Schwinger functional by taking a logarithm of that, and this delta sk is basically the regulator term, which is a quadratic functional, and it is given by this, and this rk is basically the regulator function, which I shall come in a moment. And from this Schwinger functional, scale-dependent Schwinger functional, one can construct the scale-dependent modified effective action, which is this. And this is the starting point of everything. Once you have this scale-dependent effective action, what one does is one obtains, one gets and tries to, or one derives an exact equation for this scale-dependent effective action. So here P is nothing but log K, and this is the exact non-perturbative flow equation. This is the RG flow equation for the effective action, and this is all. This is in the quantum field standard quantum field theory regime. When you apply this equation or this formalism to gravity, what you get is an equation of this kind. And here there are many terms. If you at the end of the talk, if you are interested, I can answer or explain some of the terms here. But this is the equation, RG flow equation, that you get in gravity. And from here, now let me just tell you something about the regulator function. The regulator function that I showed you in the previous slide has this form, where this R0 is something important. One chooses the form of the regulator function to be this. It is smooth and satisfies the condition that at z is equal to 0 it is 1, and z equals infinity, z equal to infinity it is 0. This basically implies that when for z is equal to 0 means p square is much smaller than k square, and therefore this function RK p square goes as k square. That is, the regulator spins all the modes smaller than the momentum scale k in a mass-like fashion, and the regulator function is 0 for p square greater much larger than k square. That is so there is no effect of the regulator term at all, and it means basically that all the fluctuations with momentum p square larger than k square at the cutoff scale are included in the effective action. Now we have the denormalization group equation in place for the effective action. One has to solve that equation. That is the next step. And how to do that? The way to do that is to take an ansatz for the effective action. So you take the simplest ansatz for the effective action functional that one can take is the following, where you take this g to be a function of k, which is scale dependent now, and if you take that and plug it into the RG flow equation for the effective action functional, this now leads to the running of the Newton's constant and the cosmological constant, and these are the equations. And this was first derived by Reuter in this paper in 1999. And if we are close to the k is equal to 0 point, which actually turns out to be a Gaussian fixed point, a trivial fixed point, then there exists power series solutions to these flow equations, and you can write it in the power series solutions can be written in this way. So you can see that the Newton's constant and the cosmological constants are now functions of this scale. So this is the starting point of our analysis. Now we go to our work. I think I have a little more than 5 minutes, right? So I will be able. I think I'll be able to finish with 5 minutes. So you have more than 10 minutes. More than 10 minutes. So then I have sufficient amount of time. So now I come to the type 1 cosmological model. The anisotropic cosmology described by this model is given by this metric. And so this is the binary type 1 metric. And we take the energy momentum tensor of the perfect fluid, which is this. And from this, we now write down the Einstein's field equations of GR with time varying G and time varying cosmological constant. Now you may ask, so far I have shown that G and lambda are basically scale dependent, they were momentum dependent, but how come it is now time dependent? From where does time come into the picture? But I will explain that in a moment. But let me just tell you for the time being, another question that you may ask at this point is that how do you write such an equation? Does it follow from some action principle? The answer is no. What we simply do is, we know Einstein's field equations, and from Einstein's field equations, what we do is we just improve Einstein's field equations by replacing Newton's constant by this time varying G, and replacing the cosmological constant by time-varying cosmological constant. So this is an improvement of the Einstein field equations. This is not a derivation of the Einstein field equation from an action principle. But one could have also improved the thing at the level of the action and then studied the entire thing. But this is not the path that is being taken at this moment. So if we write down the improved Einstein's equations with the time varying g and time varying lambda, we can immediately obtain the equations and plug in these answers for the cosmological binary type and cosmological metric. We can immediately get the field equations, and these are the field equations. This is very trivial to compute, it's not difficult. And now we also know that the left-hand side, which is the Einstein tensor, is covariantly conserved. Therefore, the right-hand side must also be covariantly conserved. Now, and so the right-hand side is covariantly conserved, but if we also take the standard prescription that the energy momentum tensor of the perfect fluid is also covariantly conserved, then that actually leads to, I would not say a problem, but that actually leads to an extra equation, and that equation is nothing but that equation is this equation. So this follows, as I mentioned, that let me just repeat once more, that if I demand PV to be covariantly conserved, which is the standard thing to do, then it will lead to another extra equation, and that equation in the literature has been named as the consistency equation. So let me just tell you what is the big deal about this consistency equation. If you just go back to FLRW universe, so for that, these ABCs are equal, and then this equation, this consistency relation or equation immediately fixes rho in terms of lambda dot and g dot. So rho is fixed. You put it in this equation, in the conservation equation, which follows from the covariant conservation of the energy momentum tensor. Since ABCs are equal, it immediately, and also rho is known in terms of as a function of time, it immediately fixes the scale factor in terms of time. So you have obtained the solution for the scale factor without even solving the Einstein field equations. So now the question is that this solution must satisfy, or it must be consistent with the Einstein field equation. So you have to put it in one of these equations and check whether that the solution is really consistent or not. And that is why this is the consistency relation. Another part that one could have taken is that we do not demand that T mu is covariantly conserved, and that path has also been taken in the literature, and we have also taken that path in our work, which I shall not discuss today. That path could also have been taken, and that would not lead to any extra equation. This is something very important. So now, since I have shown you the field equations that I have obtained, the solutions to the field equations are the following, where this M1, M2, M3 are arbitrary constants of integration, and R cubed is basically the product ABC. Now the point is that from where does time come into the picture? Time comes into the picture because we have identified the momentum scale in this fashion. Now I will just briefly explain why we have taken, why such an identification is meaningful. It is meaningful. It basically, this k is equal to 1 by t identification basically means that by the time the universe has reached the age t, all fluctuations or frequencies smaller than 1 by t should not play any role. And this justifies that a cutoff, the choice of the cutoff k can be indeed taken to be as inverse of the cosmological time t. This is one point, and this is the path that has been taken for FLRW universe in the earlier studies. But here you will find that we have taken the cutoff to be 1 by t square, and 1 by t cube. Why is this? Because had we not taken these other two terms, then we would have observed that we could not set, our solutions were not consistent. So it would violate one of the equations. The solution would not be correct. So we are forced to take such a cutoff. And once we take this cutoff, you can immediately plug in this k in terms of t in the equations that I showed you for gk and lambda k, and that gives us gt and lambda t as functions of time. And now one has to close the entire system of equation by choosing an equation of state for the pressure, and this is taken like this. The scale factor product of the three ABCs is given by this. Energy density can be immediately obtained from the consistency condition as a function of time, which is this. And this now leads to the consistency relations. For radiation, it turns out that we have this one consistency condition is this, the other is this. it immediately follows, if we use this equation in this equation, it immediately follows that this thing L squared, this left hand side must vanish. Now the point is that if L is not equal to 0, this L is, by the way, an integration constant that occurs in the solution for the scale factors. If it turns out that L is not equal to 0, then beta here must be complex. But beta appears once again in the solution of the scale factor, and therefore if beta is complex, then the scale factor is complex, which is not possible physically because the scale factor must be real, and therefore the only choice is that L is equal to 0. Hence we see that all the directional Hubble parameters must be equal, that the universe must be FLRW in the presence of radiation. So it basically means even if we start with a type 1 anisotropic model, it will ultimately flow to an isotropic model of cosmology, which is the FLRW model at late times for radiation, which we work with radiation. And the same observation holds again for dust. For dust means pressure is equal to 0. But the interesting thing comes out here, if we take stiff matter, for stiff matter, once again, we can follow the entire procedure, we can compute the scale factors, we can obtain the consistency conditions, which are these two equations, and from this equation, we can write L in terms of this, L in this fashion, and since the directional other parameters A dot by A, B dot by B, C dot by C are here, we get the following condition from the above equation that this must be greater than or equal to 0. And I just leave, if this is equal to 1 by 6, then once again we go back to the previous conclusion that this must be equal to 0, which implies that L must be equal to 0 by the same argument that we have earlier. But if this does not saturate, if this equality is not saturated, then something interesting occurs. We can calculate the directional Hubble parameters. We observe that for large beta we get a Krasner type solution. What do I mean? I will just explain in a moment. For large beta, expanding directions. So you see that these terms are positive for large beta, but this term is negative for large beta. So it means that for large beta, the expanding directions will involve the scale factors A and B, and contacting direction will involve C. So there are two expanding directions and one contacting direction. And so that is what is meant by a Krasner-like universe. So it means that we get a Krasner-like universe for this stiff matter. So let me just come to the summary of my talk. We have studied the anisotropic binary type 1 cosmological model for late times, taking quantum gravitational effects into account. The consistency conditions following from Einstein equations indicate that the binary 1 anisotropic cosmological universe eventually evolves into a FLRW universe at late times, filled with a perfect field with equation of state this, where the equation of state parameter lies in this range. And for omega is equal to 1 for stiff matter, which was we observed from the consistency conditions that the solution does not flow to the isotropic FLRW at late times. Rather, there is a possibility of getting a Krasner-like universe. So with this, I would like to stop. Thank you very much.
Thank you. Is there any question from the audience here? Still connected.
26.
Is there any question from the online audience?
Can I ask something, Amitabh?
Yes, please.
Sure.
No, I didn't get what was the relation with the first part of your talk where you discussed about the functional renormalization group.
Dr. Can you be a little bit louder? I cannot hear you.
What I'm saying is that what I did not get what is the relation between the first part of your talk.
I see.
Where you talked about the functional renormalization group and then you switched over to this. Yeah.
Yes, the relation is quite simple in the sense that I just wanted to tell you briefly about the functional renormalization group approach to quantum gravity, and the consequence of such an approach actually leads to the running of the coupling constants. Here, in this case, for gravity, it leads to the running of the Newton's constant, gravitational constant, and the cosmological constant. And what we have the connection of this part of the functional renormalization group approach to the second part, which is our work. we actually use this running. We actually look at the consequences of this running of the Newton's constant and the cosmological constant to study and see its consequences in a cosmological model at late times. So this is the connection. We are using the solutions for the flow equations. We have some flow equations for the Newton's constant and the cosmological constant, and we are using those solutions. And we are using those solutions. We are looking at the cosmology of the binary type 1 model, cosmological model at late times. We could have done the same thing at early times also, but then the important thing is that then we could not have used the solutions, the power series solutions that we are using now. The power series solutions that we have used in the analysis, they work only for late times, for a low cutoff scale.
So you're saying you're using GT and lambda t from that part, right? That is what you're saying.
Yes. We are using the forms of GT and lambda t, which has actually been derived from the functional renormalization approach. They take into account the effects of quantum gravity. And now we are using that to study some cosmological model at late time, and we are trying to see how does that model flow.
Okay.
Very nice talk, Shunandal. I was, however, not fully conversant with this approach. It's a nice approach, it seems. I'm just wondering, you are changing the scale because you are actually integrating out certain modes above a certain threshold value of the scale. So is there a background metric you need, which is non-dynamical, which you don't integrate over?
Well, if we go into the details of, first of all, the first comment that you made is very interesting, that this approach, actually, most of the people who work here is at least in India, not very familiar with, but this is a very, very sound approach that has been developed over the last 30 years, and there has been a lot of work actually. And
yes, I know that. Yes.
And the second part that you are asking, just the background thing. If we look at the derivation of the flow equation for the effective action, and then the solution of the flow equation, if you just try to look at the way in which the differential equation for the effective action is derived, you will see that the first step in the derivation is you need to choose a background, but you don't need to specify what the background is. So the first step is that you expand the G, the metric, in as G bar mu, which is a background metric, and put some fluctuations on top of that. But the important point is that you don't need to specify what the form of that background metric. The entire analysis works without using the form of the background metric.
So the scale is measured with respect to the background metric, right?
Exactly.
Okay. Thank you very much. Yeah, that's great. Yeah, that's what I thought. Yes, great.
Any other question? If not, then let's thank the speaker again. So we go to our next speaker, and this is a speaker from across the world. The speaker is Horacio Nastase from IFT Sao Paulo, and I see that he is already here. And welcome, Horacio.
Thank you.
He is an invited speaker, so his talk is of 40 minutes, and he will talk on learning from Penrose's limits of less understood gravity work. Please share your slides.
Yeah. Is it okay?
That is not
coming yet. Okay, it's coming.
Now it's okay?
Yes, sir.
Yes.
Okay, good. So I would like to thank the organizers for inviting me to speak at this conference. So here I will talk about some recent work with a student, Marcelo Barbosa, and this is following work from a few years ago that I will describe at the beginning. So the work is trying to find a little bit more about gravity dual pairs that are less understood via application of the Penrose limit and obtaining the PP wave correspondence. So, so as a summary, I'll first introduce what I'm going to do. Then I will review quickly the Penrose limit and the PP wave correspondence. And I will follow with the three specific cases. First, the duality between Guarino-Jafferis Varela background and the Super-Mills-Chen-Simons in 3 dimensions, and take the Penrose limit of that. Then the abelian and non-abelian T-duals of ADS5 cross S5 and their Penrose limits. And finally, the duality found by Juan Maldacena and myself in 3 dimensions, and the Penrose limit of that, which is the most recent work. And then I will conclude. So in ADS-CFT, you usually has some supergravity limit and some non-perturbative field theory coming from it. And the best known cases are the ones with maximal superconformal symmetry, like ADS5 cross S5 versus N=4 Super-Mills, or ABJM versus ADS4 cross CP3. But the advancement of the Penrose limit was that on the gravity side, we obtain actual strings as opposed to supergravity modes on PP waves. On the field theory side, we have a large charge sector, denoted sometimes as BMN sector, on which we obtain some version of a spin chain. Now, the advantage is also that when we have a complicated gravity dual, the Penrose limit gives a simpler PP wave, and correspondingly we have a simple field theory sector that's easier to describe. So because of that, we can learn things about the field theory and test our understanding of the ADS-CFT duality. So now, to go to specific examples, whereas in N=4 Super-Mills, we have usually a correspondence between a complete equality between quantities found at zero coupling and at infinite coupling. In ABJM, there is one non-trivial function of the coupling that has different values at small and large couplings. We will, in examples that we were going to describe, first in the JGV versus Mills-Chen-Simons duality, which is on the gravity side a warped and squashed ADS4 cross S6, obtained as a fixed point on n D2 branes with Romans mass. And on the field theory side, n=2 Super-Mills-Chen-Simons with SU3 cross U1R global symmetry. In this case, we will find several functions of non-trivial functions of the coupling. On the other hand, in the case of T-duals of ADS5 cross S5, the field theory in that case is even less understood. So what we will really find are predictions for the field theory. And we'll find some interesting behavior. For instance, in non-abelian case, we'll find a deconstruction of the field theory, which means the appearance of extra dimensions at intermediate energies. And finally, in the case of the solution of Maldacena and myself, which is also in 3 dimensions, SUN-Chen-Simons with spontaneous supersymmetry breaking obtained from 5 branes on S3, then we'll find that there is some sort of mismatch between low and weak coupling, but we will at least obtain some predictions about the behavior with lambda. So what's the Penrose limit? The Penrose theorem says that you can always put the metric in a form like this if you go near a null geodesic defined here. And then if you rescale the coordinates in this form of the metric, as one of the null coordinates stays the same, one is rescaled with 1 over r squared, and the transverse coordinates with 1 over r. And you take r going to infinity, then you obtain a PV wave in so-called Rosen coordinates. And after a coordinate transformation, you obtain them in Brinkmann coordinates, where there's, beside the flat metric, there's the addition of this factor, h times dx plus squared, where h is quadratic. So for a general PV wave, h would have a general form, but in this case, in the Penrose limit, we find this form. The interpretation of this is that while we boost along a direction, we can take the scale of the metric to infinity. And so equating the boost with a scale and taking it to infinity, we obtain the PV wave metric. Oops, no, what did I do? Sorry. In the case of ADS5 cross S5, in the Penrose limit, we obtain the maximally supersymmetric PV wave. And unlike in this description of the Penrose theorem, where we needed to obtain the Rosen coordinates first, in this description, doing the procedure in global coordinates, we obtain directly the Brinkmann PV wave. So expanding around the null geodesic situated in the center of ADS and at some equator of S5, moving along the equator in the direction psi, we find the metric described here. And in n equal 4 super m mills, because of the identification of the energy, the gravitational energy with the generator of the tau direction, sorry, the energy in field theory with the generator of the tau direction, and the U1 charge with the generator of motion in psi. That means we can identify these with the conformal dimension and the U1 charge that rotates two of the scalars. Then we find that P with minus up corresponds to delta minus J, and P with plus up corresponds to delta plus J over R squared. And since these quantities are supposed to be fixed in the limit we want to take, that means that delta is approximately equal to J and goes to infinity like square root G squared N. Another way of saying it then is that J over square root G squared N is fixed while the quantities go to infinity. So on the PV wave side, if you consider a string action on the PV wave, we obtain, oh, sorry, this was all, I typed this wrongly here, but it's integral d tau, integral d sigma from 0 to 2 pi L prime P plus. So we obtain the string action, which is just a free action with a mass term. And the frequency modes for the oscillators, the string oscillators, are given here. So there's this square root formula. So whereas the momentum is n over alpha prime P plus, the frequency is square root 1 plus n squared over alpha prime mu P plus squared. And this gets mapped to in n equals square mills to the anomalous dimension minus the charge being equal to square root 1 plus this quantity which was held fixed, G squared n mills n over J squared times n squared. And choosing the scalar Z, which is phi 5 plus I phi 6, so it's charged on the U1R, then the string vacuum corresponds to the string vacuum with momentum P plus corresponds to the operator. Oh my, again, trace Z to the J. I'm sorry about this. so to the operator trace z to the j with some normalization. And on it, we can consider insertions of the other scalars phi m and of derivatives of z, covariant derivatives. And these would correspond to acting with string modes at level n and in the direction m. So these insertions, if we consider them with a momentum n around the trace, this corresponds to level n in string oscillators. Now, the interaction Hamiltonian in super Yang-Mills, which is just the commutator squared, sum over I and j, defines a certain action on these operators, so-called BMN operators with insertions. The way to understand this, since we have a conformal field theory, if we map the plane R4 to S3 cross R, then we obtain a quantum mechanics. And in this quantum mechanics, we have creation operators that correspond to each of the fields. And if I call B the creation operator for Z, and A the creation operator for the insertion phi, then I can define a new kind of state, the one that I will call A dagger, which stands for this object with insertion at a certain point. And then this new A dagger is a new kind of, it's not a usual kind of oscillator, but so-called Kunz oscillator that satisfies a different algebra. But other than that, the Hamiltonian is something that looks pretty familiar. It's a free part, A dagger A, and then an interacting part that is basically a discretization of a field, of the derivative of the field squared, A plus A dagger being the field. So this is phi at L minus phi at L plus 1. So this is phi prime squared here with a certain coefficient. And we can also obtain an identification between the number j of sites in here and the length L of the string. And this Hamiltonian then is written as phi dot squared plus phi squared, corresponding to A dagger A, plus phi prime squared coming from this interaction part. And going to the action, we see that we obtain exactly the action of the string on the PP wave, which is written here. So in other words, directly by considering the interaction Hamiltonian of super Yang-Mills that defines the theory, we can obtain the action of the string on the PP wave, making an identification between the two. And moreover, a direct diagonalization of this interacting Hamiltonian gives the frequencies that directly map to the frequencies of the string on the PP wave, written in this form. This is the more general form where, so unlike before, little n can be large. So little n over j can be finite. So this is the complete form of the frequency of the string oscillator. On the other hand, and this was obtained directly from the interacting Hamiltonian of super Yang-Mills. On the other hand, we can do a more concrete calculation. We can do a one-loop calculation. So one-loop Feynman diagram, specifically, if you consider the BMN operator described as this line here with fields Z, most of the fields Z, and one insertion of field phi. And here another operator. So this is operator at 0, this is operator at x. And we can consider this Feynman diagram. where for the 2-point function, where we have free propagators between all the fields except one interaction involving phi. So this is phi and z, and this is the other Feynman diagram. By calculating these Feynman diagrams, which are one-loop Feynman diagrams, we can interpret this as the action of the interacting Hamiltonian acting from the previous case, this interacting Hamiltonian acting on operators. And another way of thinking about it is as the one-loop dilatation operator. And finally, another way of, and by doing so, we obtain the one-loop expansion of this formula. That is this term with a factor 1/2. By expanding the square root, we get first order term is this times 1/2. And finally, this one-loop calculation can be reinterpreted as a spin chain Hamiltonian acting on a spin chain. And this can be generalized to the so-called SU2 sector, which can be thought roughly as going as this case, our case, the BMN case, going beyond the dilute gas approximation. And one obtains, in this case, the Heisenberg Hamiltonian of the XXX spin 1/2 chain. Okay, so this is a revision of what we obtain in super Young males. But in a general system, we'll take the Penrose limit and we obtain a PP wave in the gravity side, and there are large R-charge sector in the field theory. And you calculate delta minus J for these operators, and you obtain a dilute gas spin chain. And we try to match this with modes on the PP wave. So we do this first in the case of JGV versus three-dimensional super-Hamilton-Simons duality. So the gravity dual is written in here. And the field theory, this is just the metric, so ds squared. And in the field theory, we have the infrared fixed point of ND2 branes with Raman mass, which gives an n equal to super Yang-Mills-Chern-Simons theory with gauge group SUN, with some n equal 1 vector field and 3 n equal 1 chiral superfield. And then the action is composed of a Chern-Simons term, a matter term, and a superpotential term, the superpotential being written in here. And the theory has U1 or SU2 R symmetry times an SU3. The interaction potential, there's a conformal part which is a sextic part written here, plus a non-conformal part, which is the same roughly as in n equal 4 super M Mills. By some complicated assignments of mass dimensions, we find that the theory in the infrared must, so one way of describing it is by putting these scalars to commute for, so phi I commuting with phi j for all I different than j. These are SUN matrices, remember? But that means that we can still have phi I and phi I bar be non-zero, and even phi I with phi j bar be non-zero. On the gravity side, we have null geodesics. So we have to obtain PP waves as going close to null geodesics. And the null geodesic condition gives this gamma to be 0 for all I, where lambda is the parameter along the geodesic. But if, moreover, the geodesic goes in an isometry direction, then the condition is this one. This metric has 3 isometry directions, angles sigma, phi, and psi. where sigma and phi belong to a CP2 and psi doesn't. And if we consider, and the useful motions are in psi, sigma, and phi, and also in phi plus sigma. If we consider the motion in psi, we obtain this kind of PP wave, which is not that unusual. We have a quadratic term multiplying dx plus squared. Yeah, I'm not sure why I obtained here everywhere obtained delta instead of d, but anyway, this is dx plus dx minus. And we can calculate the closed string eigenmodes, and not surprisingly, they're still of this form of a square root of constant plus n squared over mu alpha prime p plus squared, constant being in one case 1 and in the other 1/4. In the second case, we obtain a slightly more complicated PP wave, because now we have this quadratic term, but we also have a term with cosines and sines of x plus. In the third case, again, we get something with cosines of x plus, cosines and sines of x plus. And in the fourth case, we obtain something, well, intermediate, let's say. So we have a quadratic piece, and then we also have a piece that is off diagonal. But what all these cases 2, 3, and 4 have in common is that a subset of coordinates, for a subset of coordinates, the string oscillation modes are of the simple mode with square root of a constant plus n squared over mu alpha prime p plus squared. For the open string modes. Now, for the closed string modes, in the first case described here, in the spin chain case, we've seen that phi I and phi j are non-commuting. And phi I and phi j are 0 commuting for all I different than j, which corresponds to the fact that this part, the non-conformal part of the Hamiltonian, is 0, and we're left with a conformal part, which has only phi I with phi I dagger. And in that case, we obtain again that the string vacuum corresponds to the trace z to the j, and insertions correspond to phi m bar, and covariant derivative and z bar now. So that's the insertion of z bar is unusual with respect to n equal 4 spam mills. And again, string oscillators have the same form. However, what we obtain is that there are, so in the calculation of the anomalous dimension, delta minus j is the tree form plus a certain function times lambda over 2. And so we have 3 different functions of p, which together with the lambda over 2 give a function of p and lambda. So the match that we obtain to between the Spam-Mills case and the gravity solution is only by introducing non-trivial functions of both lambda and p. On the other hand, in the case of open string chains, open string spin chains, it's even more puzzling. So for an open string on the giant graviton D4 brane, the maximal giant graviton corresponds to this operator. And the open strings that we're interested in are charged under different U1 then that we'll call J bar, different than the J for the closed strings. And so we correspondingly we find the vacuum as inserting something that is charged under J bar inside this determinant operator. We get some operator like this. And the excitations are by introducing now introducing insertions inside this w to the power j bar. However, what we find is that now, even at tree level, only the covariant derivative insertion match, and the other ones don't. So the open string case in this case doesn't seem to work at all. So that seems like a puzzle. And so from that point of view, so we can consider. So well, it is actually a puzzle. So we don't know what to do, but it means that we have to learn something more about duality in this case, and the Penrose limit stresses this fact. In the case of T-duals of ADS5 cross S5, we have, in the case of abelian T-dual, we have this metric, and the proposed field theory dual is a circular quiver with vectors at the node and hypers between consecutive nodes. And there are several possibilities for Penrose limits, but one interesting possibility that tests the T-duality is in the direction in which we did the T-duality, in the direction of psi. However, to avoid some pathology, we need to add a motion in an extra direction psi. So in that case, we find a metric that is a little bit that is somewhat simple. So it has also quadratic pieces, and so omega squared is again some constant plus the same n squared over mu alpha prime t plus squared. And in a non-abelian T-dual case, the metric is a little bit more complicated now. And the field theory dual is an infinitely long quiver that can only terminate if I consider a UV completion of the gravity dual. And the Penrose limit is slightly more complicated. So we have the quadratic piece, but now we also have this piece that contains a motion in this coordinate row related to u. And the closed string modes, they are the modes in direction r bar omega 3 and x and w are of the usual type, the constant plus n squared over mu alpha prime t plus squared. But in the other direction depends on the Rotilde variable, the one on which we did the T-duality, the non-trivial coordinates. In the field theory, as we said, we have a vector n equal to vectors at the nodes and bifundamentals between the nodes. There's a certain superpotential. But so we can write in this case a vacuum with momentum p and winding, and a vacuum string mode with a momentum p and winding. And in the field theory, the winding corresponds to winding around the quiver. Again, we can make insertions of covariant derivative and the scalars into the trace, but now the trace has this extra property that is a trace going around the quiver. And if we want to add a mode number n to the oscillators, so a level n oscillator, we also need to include the winding such that the winding is the sum of the momenta. Because while winding around the string, that also corresponds to a momentum. In this case, at the abelian case, we have the mismatch already at so-called tree level between the anomalous dimensions of the operators. But the observation is that in this case, the quantity g squared over k is no longer finite, unlike before the T-duality, where similar kinds of operators were were considered. So that means we must consider the theory beyond tree level, and that is something to be understood further. In the non-abelian case, what you obtain is a certain RG flow in the light cone time. That means on the world sheet, in the light cone time u, from u equals 0 to u equals infinity. And we have also a certain deconstruction, meaning that there's an extra dimension appearing in the field theory at some intermediate coordinate u. So we have learned something about the field theory, but there is much more to learn by doing this Penrose limit. So finally, let me come to the case we did recently, the case of the duality of Maldacen and myself, which corresponds to 5 branes on a 3-sphere with a twist that gives this gravity dual, where this is defined by 3 functions of rho that obey some differential equations, so no analytical solution. But in the infrared, they have these values, and in the UV, they have these values. And this theory has a dynamical or spontaneous supersymmetry breaking, because the flux K must be greater than n/2 in order to have supersymmetry, but if we have less than n/2, we have supersymmetry breaking. So this gravity dual is obtained for in the case that the 5 branes are NS5 branes, but we can go to a S-dual picture in terms of D5 branes by putting some factors of the dilaton. The field theory is n=1 supersymmetric with and the Chern-Simons term. And then there's massive fields with the mass of the order of 1 of the radius of the sphere. The radius theory can be is just gauge field like gauginos, and the gauginos can be integrated to give pure Chern-Simons. However, it turns out that we cannot neglect the massive modes. So we have to consider the 6-dimensional theory, which is n=1 vector plus n=1 hyper. And when we Kaluza-Klein decompose on S3, after the reduction from the gauge fields, we have under the various symmetry groups, we have a component that corresponds to scalars. This one is the SO21 representation, so scalar. Scalars become scalars again. And so after the twist that identifies 2 SO2s, we have scalars in the representation 1, 3, 1, and scalars from the original scalars in representation 1, 2, 2. So both of these are massive scalars. So naively, we shouldn't consider them, but actually it turns out we should consider them. And the Penrose limit, again on an equator and moving on an equator and being at the center at rho equal to 0, like in Nicoll-Force-Spaniel's case, but now also having a component on the S3 on which we wrap the 5 branes. So the Penrose limit gives this PP wave. And the string modes look complicated, but if I have here various oscillator numbers n, but if I take them n1 equal to n2 equal to n, they become very simple. In order to match the field theory modes, we consider that the scalars that come from 6-dimensional scalars decompose like this in terms of z and w, complex values z and w. And we can make an identification of the various field theory modes. So, or identification of delta minus j, now delta minus j minus a certain constant E0, with the corresponding values of the Hamiltonian for the string at the tree level. So we can identify the field theory insertions with string oscillation modes. And in this case, we have, again, field theory operators that are traces of many insertions of field theory modes. So trace Z to the J in this case. But in this case, since we're talking about a theory with less supersymmetry and scale dependence, by an analogy with a 4-dimensional case where we would have something like n equal 1 super mils, these are some sort of circular hadrons-like objects. So they were called, they were previously called annulons in this specific case, but otherwise the same idea holds. And again, insertions of the fields correspond to insertions inside the trace. And also, again, we consider the one-loop anomalous dimension corrections coming from the interaction Hamiltonian using Feynman diagrams, the same Feynman diagrams, actually, just that now in 3 dimensions. And we obtain delta minus J minus the constant E0, again, a 3-level object that matches as before, plus a correction. But this correction doesn't quite match what we get from the string theory side. But there are several reasons for that. One being that we are in the UV, because this object becomes perturbative only in the UV when x is small, goes to 0. This coupling constant g squared n x over j squared becomes perturbative only in the UV. But the field theory was actually in the IR, so there's some mismatch. This goes together with the fact that there's a smaller supersymmetry, and we expect now also the function of the coupling, the effective coupling between the small coupling and large coupling, which in 3 dimensions corresponds also to UV versus IR. Also, there's a component of the UN charge J that is in the direction that is not isometric. And also, in principle, there are other Feynman diagrams that we have neglected that could perhaps change this result. So in any case, the conclusion is that we have to learn more about this case. So to conclude, the Penrose limit gives a string on a PP wave corresponding to a large charge sector on the field theory. And in the simple cases, like ADS5 cross S5 and ABJM, we obtain matching, although for ABJM, we need to consider a non-trivial function of the coupling. But in more complicated cases, this allows us to learn about field theory, about the field theory that is dual to a certain gravity theory, and about the holographic map between the two. So I haven't described too much. I've described certain puzzles and possible corrections, but they nevertheless teach us something about the duality. So specifically in the JGV versus Chen-Simons versus superior Mills Chen-Simons, we have for the closed strings, we have certain functions of the coupling. And for the open strings on the D-brane, we have a certain mismatch. That's a puzzle. In the case of T-duals of ADS5 cross S5, we identified the operators, but found already a mismatch at the 3 level. And I put it in quotes because we found that actually, afterwards, we found that actually we're in a different limit. So the 3 level is not so 3. And in the non-abelian case, we found an interesting behavior of an RG flow and deconstruction at intermediate values of light time. And the duality of Maldacena and myself, we find a match at 3 level, but mismatch of the quantum corrections. which we still need to understand, but I gave you several reasons for that. All right, so that is all. Thank you very much.
Thank you, Rajiv. Are there any questions about the talk? Okay, Shwanda.
Thank you very much for your nice talk. So I have a nice question. Usually, we usually say about this the area safety, but when we use the area safety duality, we usually say something about the strongly coupled field theory by looking at a weakly coupled gravity theory.
Yeah, it's still the case here. That's what I mean. So we do calculation in a gravity background. I mean, it's a string action, but it's still in a gravity background. So it's weakly coupled. Yeah.
My question is the following: that is it possible the duality should work also the other way around? So is it possible really to, if you consider the field theory to be a weakly coupled field theory, then is it possible to
well,
strongly coupled gravity theory? Is there any progress on these lines?
Well, that's an important question. I mean, that's sort of a holy grail in some sense, right? Because in some sense, what would mean is that we will have a definition, or perhaps perhaps even more boldly, a test of the strongly coupled gravity theory. So, so in the case of n equal 4 super Mills, I wrote a small attempt at, well, I called it a physicist proof of ADS-CFT duality a few years ago, where I tried to to sharpen a little bit the what we did in the case of the BMN paper. But anyway, so there's not, even there I couldn't say much about how to define gravity. But there is one exception to that, one notable exception, which is actually very important to my mind, and I'm surprised that more people don't work on this. This is the so-called holographic cosmology. So this, I mean, many people have tried to do various holographic cosmologies, but the specific description, approach that I describe is one first defined by McFadden and Skenderis in 2009. So so this is a little bit of a phenomenological approach. So correspondingly also phenomenological ADS-CFT if you want. So basically you assume ADS-CFT is valid by looking at various examples, and then assuming the map is still valid, what you learn. So in this case, the specific issue that we want to understand is it possible to have at the origin of our universe, at the Big Bang, a cosmological theory that is strongly coupled? This is important because even in the usual descriptions of inflation, if you have a certain number of E-folds, I think beyond 70 E-folds or so, I don't remember the exact number. So then if you go back to the origin of this inflation, the origin of the 70 E-folds, you have already strong gravity. So you know that perturbative treatments like the usual deflationary ones don't work. So what do? Well, ADS-CFT is one thing you could think of, but you can only do it in this phenomenological way, assuming that the map still works, and then do a perturbative calculation in field theory, and then you can learn about this non-perturbative cosmology. So this has been this approach has been developed by many people, including myself. And it's a very promising one, I think. But in terms of, well-defined gravity duals like ADS5, process 5 versus Super Mills, no, we don't know in that case.
Thank you very much. Any other question? Anything from the online audience? Okay, so if there are no other questions, let's thank the speaker again.
Thank you.
And we have the last talk for this session coming up. And this is another speaker who has joined us from across the world, Alicia Platania.
Hi.
Hello, Alicia. And she will be speaking on sifting quantum black holes through the principle of least action. Alicia, you have 40 minutes.
Thanks. Wait a second. So I can share my entire screen, I guess. Okay, can you see my presentation?
Yes.
Yes. Okay, great, thanks. Yeah, okay, so let me start by thanking the organizers for organizing this conference and also for having invited me to speak. So as already mentioned, so I will be talking about this topic that is based on a recent paper that I have put on the archive last week. And the general topic is about finding actions, effective actions, specifically producing some of the proposed alternatives to classical black holes. And so the starting point is the observation, and what one would, I think everyone would agree, that singularities that are typically arising in general relativity in cosmological context and inside black holes entail a loss of physical predictability, and from which the saying that general relativity predicts its own background, and therefore they should be resolved by some form of new physics. And we don't know exactly what form of new physics will provide such resolution. It could be quantum gravity, or it could be some form of exotic matter. But something has to change in our description of gravity and of black hole physics. And in particular, there have been several alternatives to classical black holes, mostly arising from model building. So one tries essentially to replace the classical singularity or the classical black hole with something that makes sense physically. And among the proposed alternatives to classical singular black holes, there are various regular black holes, so the Hayward, the Minikova, Bardeen, and so on, solutions, wormholes, but also compact objects with sufficiently small compactness, such as fast balls that arise in the context of string theory, but also gravastars, boson stars, anything that could mimic a black hole from outside and look similar to it from far away. The question is whether any of these solutions can arise from a theory of quantum gravity. So here I'm assuming that the singularity resolutions or whatever could arise from a theory of quantum gravity. So I'm forgetting about matter, exotic matter, and focusing on the question of whether one of these solutions can arise from quantum gravity, and in particular from a principle of least action in specific theories. And now the motivation of my work and the context comes a little bit from my background, my expertise in one specific theory of quantum gravity, that is asymptotically safe gravity, and I will talk about it in a second. But it turns out that the final consideration of my talk might be slightly more general than that. So let me discuss black holes in asymptotically safe gravity. Asymptotically safe gravity is one proposed theory of quantum gravity, and it is one of the most conservative, I would say, since it is based on essentially quantum field theory. And the only new ingredient that one would put in to make sense of gravity as a quantum field theory is the notion of non-perturbative renormalizability that was introduced by Wilson in the 70s. And it relates the renormalizability of a theory with the existence of UV attractive fixed points for the renormalization group flow of quantum field theories tied with a finite number of relevant directions, since this would be related to predictability. And it was proposed by Weinberg some years after Wilson's proposal that eventually gravity might make sense as a quantum field theory if it is non-perturbatively renormalizable in the Wilsonian sense. And it seems that from the computations that have been performed so far, that of course are performed within approximations, that the gravitational renormalization group flow seems to have this interacting fixed point, and that there are a finite number of relevant directions. But now, how about quantum black holes, or in general quantum corrected solutions in quantum gravity from the perspective of asymptotic safety? This is related really to the formalism of quantum field theory. So in the context of quantum field theory, if we want to make sense of gravity as a quantum field theory, resembling quantum fluctuations would essentially be equivalent to resolving the path integral, a path integral over all possible metric configurations, starting from a certain Bayer action. And a very important object in this formalism is the effective action, that essentially would replace the Bayer classical action with another action, the effective action, that is seemingly classical, but includes all quantum fluctuations. And this formalism still holds as soon as one is in a quantum field theory, even replacing the metric with alternative gravitational degrees of freedom. And the fully quantum solutions in this particular approach would arise essentially as solutions from effective field equations that arise from that are obtained from the effective action. So this action is looks like a classical action, but if it is obtained by integrating out all quantum gravitational fluctuations, then it is fully dressed, and therefore the solutions that one would find from these fully dressed field equations are the fully quantum corrected solutions of the theory. State of the art is that the effective action is not known yet, even though there are groups making progress on finding approximations to the effective action that could be used in the future to compute at least approximations to quantum black holes and quantum cosmology. But now the question that I have been focused in a sense is a different one that attacks the problem from a different perspective. So say that I can come up with an effective action whose field equations give me the full quantum dynamics and the fully quantum corrected solutions of the theory. On the other hand, there are already proposed alternatives to classical black holes. And then if quantum gravity then is to be key to singularity resolution, then regular black holes, compact objects, and wormholes should arise as effective solution to fully quantum dynamics dictated by a quantum effective action. And this should hold, I would say, at least in a continuum approach to quantum gravity, especially at large distances where any quantum theory of gravity is supposed to reconcile with quantum field theory or effective field theory description of gravity. So in a sense, the concept itself is a little bit more general than a simple asymptotic safety argument. The language might be different, the symmetries might be different, of course, in other theories, but the concept should be pretty general, at least at large distances. And now, so the focus questions of this talk are the following. So first, can alternatives to classical black holes that have been proposed can arise from a principle of least action in quantum gravity? And also, if I take a given proposed metric, say the Hayward or Bardeen black hole, what is the corresponding generating effective action? Now, these questions in general are extremely difficult to solve, to answer. But some constraints could be extracted from the asymptotic behavior of these solutions. And as I will show you, they might already be pretty strong. And the reason why one could analyze the asymptotic behavior is that many of the proposed alternatives to classical black holes share a similar asymptotic behavior. So here I'm showing you just two examples, that of regular black holes. For instance, this specific example is the Hayward solution, or the case of regular black holes or wormholes like the Simpson-Visser spacetime, which are regular alternatives to classical black holes with very different metric coefficients. But asymptotically, the structure of the metric coefficient is that of Schwarzschild, essentially, with the standard 1 over minus Schwarzschild radius over R term, plus corrections, subleading corrections that are written as 1 over a power of the radial coordinate. And this also holds for other modification to Schwarzschild black holes. They do not need in general to be regular in the center. So any modification to Schwarzschild should be subleading in the at large distances. and so it should go as 1 over r to some power, not necessarily integer. This does not apply, obviously, for black holes like the Diminikova black holes, whose metric coefficients are not algebraic. So these type of considerations only hold for modifications that are algebraic in the metric coefficient. And of course, there are pros and cons in this approach of considering only the asymptotic behavior. The cons is that it is still far from answering the question of finding the full effective action that generate a given proposed metric. But in a sense, it is also more powerful for the reason that it applies to many proposed alternatives to classical black holes, so compact object, regular black holes, wormholes, and so on. And also at large distances, one would expect that one can still use a quantum field theory approach. So in a sense, it could match also considerations from different theories of quantum gravity, since at large distances, one would expect any theory of quantum gravity to match effective field theory results. Okay, so having said so, I will focus in the following on modified static, spherically symmetric, and asymptotically flat spacetimes. So the metric is written in this form, and the metric coefficients are essentially given by these expressions. So the structure is that of Schwarzschild plus subleading corrections. And these coefficients are different, and also the exponent can be different in general. And the question is whether if one has any modification to Schwarzschild black hole that results in such a modification at large distances, what are the corresponding modifications to the effective action? So in particular, we know that the Schwarzschild term is generated by general relativity. So the R term in the action is also the Bayer, could be interpreted as the Bayer or classical action of the theory. And the rest should arise from corrections to the classical action. The question I want to answer is what type of corrections I should have in order to generate this type of large distance corrections to Schwarzschild. And the approach is conceptually easy. So one would just take an ansatz for the effective action and compute the corresponding quantum field equations. And the quantum field equations, because the variation acts linearly on each of these terms, would be written as a sum of each contribution from each term in the action. So the GR contribution and corrections at various order. And the field equation would say, the principal list action says that this must be 0. Now I replace the metric with these metric coefficients here, and I determine which type of corrections can cancel the GR contribution. And these are the corrections that would generate this type of corrections asymptotically. So in the paper, or at least in the calculation behind the paper, we used the general scaling and T and R with different powers. But for presentational purposes, I will just focus on the case where they are the same, but essentially the final conclusions are independent of this. Okay, now, what is the simplest form of the effective action that we could imagine? The simplest form is clearly a local action where this function here, that in general can be a function of the D'Alembertian. And I did not mention that this is expected because when presumming quantum fluctuations along all scale from the Bayer action at the level of the path integral, what one would generate at the effective action is typically non-local, and typically there are these functions of the D'Alembertian operator appearing here. So for instance, in a one-loop approximation, this would be the standard logs of minus D'Alembertian. And so in the simplest case, if one takes a local action, so these functions here are constant, one would have the following structure. So the Einstein-Hilbert, if I replace this in the Einstein-Hilbert term, so R, and I take the leading order asymptotic scaling of this, one would have this type of scaling, R2 minus 2 minus n, where n is precisely this scaling exponent. And if I want this to be a solution to the fully quantum field equations, then this type of term, including the coefficient, have to be cancelled out by the corresponding terms in the field equation generated by the other terms in the action. And so at the very least, one should get this type of scaling to cancel the corresponding term. But this is not possible with the Stelle term, at least if these f functions are constant, because the type of scaling that one would obtain is R2 minus n minus 4. So there is no way one can cancel the GR term. This essentially implies that one cannot obtain something like Hayward regular black holes from stellar gravity. But one could obtain in principle something like that at cubic, if one includes also cubic orders in the effective action. Because in this case, one would also generate a term that scales like R2 minus 8. And therefore, for a specific value of this power here, that is n equal to 6, one can cancel out this contribution. But of course, one would also need higher order contribution to cancel the stellar terms, since it will likely be there. And also, all the subleading contributions have to cancel order by order. And so, in a sense, having only local terms would lead to a fine-tuning of what we can have in the action and what we can have as scaling exponents, since, for instance, this local action would only work for n equal to 6. N equal to 6. More generally, so what would be the function of box that I should use if I want to have a cancellation for generic values of n? One can obviously use power counting just to have an idea of what could cancel the GR term that scales in this way. And the answer is a non-local ansatz of this form, where the function f have this type of Polyakov non-localities of the type 1 over box. And if one then performs the calculation, so takes this and with this type of coefficients and compute the corresponding contribution in the field equations, indeed one obtains this type of scaling, R2 minus 2 minus n, that can cancel the GR contribution. And this also gives a constraint on these coefficients, alpha and beta. And these are the specific coefficients for which there is a cancellation, that is, for which this type of asymptotic scaling would correspond to a solution to the quantum field equations. And if, in a sense, unexpected, surprising consequence is that for these specific values of alpha and beta, one would obtain a graviton 2-point function that is 0. So one would have no standard propagation of gravitational waves. And needless to say, this has important implications in the sense that if one focus on asymptotically flat spacetimes and on black holes that have this type of scaling asymptotically, then this type of modified black holes can only arise from a principle of least action for specific values of n, in particular n equal to 6, from a local action principle. Otherwise, for generic n, and in particular Hayward black holes, Bardian black holes would not have n equal to 6, they would have n equal to 4. In that case, one would need large distance non-localities. So at the very least, 1 over box at quadratic order, but also stronger non-localities at higher orders. And this might be visible on observational scales. That would mean that this would be essentially at odd with observations. Clearly, an exception would be the Diminikova black hole solution, since the metric coefficients are exponentials, and therefore one cannot use this type of scaling. Okay, so this leads me to my summary and conclusions. And the first statement and the starting point of my work is that in transitioning from a classical theory of gravity to quantum gravity, or more generally to a theory that includes also something that can regularize classical black holes, Schwarzschild black holes will be, or rotating classical black holes will be replaced by something else, regular black holes or wormholes, gravastars, anything that can produce something that physically makes sense and does not lead to inconsistencies. And the key question that I asked myself was whether any of these proposed alternatives can arise from a principle of the least action. And this would be relevant, in my opinion, in many approaches to quantum gravity. Obviously, in different approaches, the language would change, the symmetries would change, but at large distances, this is a question that makes sense for all theories of quantum gravity. And in this talk, specifically in this, in the work that I have put on the archive last week, I focused on the large distances, since computations are very are doable, still not straightforward, but doable. One would only obtain sufficient conditions, but are already pretty strong, and adding, say, more terms can only make these constraints stronger. And also at large distances, it is expected that one can use standard concept in the quantum field theory, and therefore, in particular, the concept of an effective action. And I focused in particular on the case of asymptotically flat spacetime. So obviously there is this caveat, even if one would expect that, given that the cosmological constant is very small, this is a good approximation. Still, one should analyze the case of asymptotically de Sitter spacetime. And I also focused on static and spherically symmetric solution whose metric coefficient admit an asymptotic expansion in powers of the radial coordinate, which is not the case for Diminikova black holes or other alternatives to classical black holes that have exponential or transcendental metric coefficients. And so first, if one use only local terms in the effective action, the best that one can produce is a certain type of asymptotic corrections. So not all proposed alternatives to classical black holes would be compatible with that. So for instance, Hayward and Bardeen black hole would not fit into this picture. And if one want to stretch that and make it work for all alternatives to classical black holes, whose asymptotic scaling as generic powers of the radial coordinate, then one needs null localities, infrared null localities that are large at large distances. And at quadratic order, this would be Polyakov terms, so something like 1 over the D'Alembertian, and would lead to so large distance null localities. And in the case of a Polyakov term, because of the specific coefficients of the of these form factors, one would also get a vanishing graviton 2-point function, which would lead to a non-standard propagation of gravitational waves, and this would be at odds with observations. And with this, I thank you for your attention, and I'm looking forward to your questions.
Thank you. Thank you, and that was a very nice talk. So, are there any questions? Are there any questions online or offline? Dr. Nandan, please.
Thanks, Dr. Catania, for a very nice talk. So, I have a very simple question. Do you think that your analysis will go through for space-times which are not asymptotically flat?
So there will be obviously additional terms in the field equations, and this could change the result. I mean, it can be extended. It is more difficult because then one cannot really use a curvature expansion of the effective action in a standard way, and one has to think a little. So it is more computationally more involved. That's why I did not start from that. But yeah, so in principle, if one buys that the cosmological constant is extremely small, that might not give rise to huge corrections should not change the conclusions by a lot, even though there should be additional constraints and additional terms.
Okay, another simple question is that I could not follow the term which you included in the effective action. There was, you had an R² term, and with that you also had a function if. You started a function, and you determined the value of the function to be some constant divided by delta. My question is, what was the delta?
So the delta is the D'Alembertian operator, so box. So G mu nu, d mu d mu.
Okay, thank you.
And that comes from the integration of quantum fluctuations along all scales.
Okay. Thank you.
Any other question? I have a small question. If you,
yes.
So, right. So the question is, you had this R² and R mu nu divided by delta, right? But if you have non-local action, if you have a non-local action, you are allowed to have more terms. How can you decide when to stop? In general, if you have a local action, then some symmetries or some other condition will tell you where to cut off the action. But if you have non-local action, then you can have higher powers of R and divided by more powers of delta. So how do you know where to stop?
Well, first of all, my analysis holds at large distances, and therefore in a curvature expansion of the effective action at large distances, one would have a small curvature in general, and therefore the quadratic terms, for instance, would be more important than the cubic ones. And obviously one can also consider the cubic terms, and we try to see what type of non-localities would give rise to that type of inverse power law corrections, and these are even stronger non-localities. So while at quadratic order one would need something like 1 over box, at the cubic order one needs stronger non-localities, so something like 1 over box to n, not the same n of the power law, but some other n that is larger than 1, and this would be even more at odds with observations. So that essentially means that not all proposed alternatives to classical black holes would work.
Right. Okay. Unless there are further questions, let's thank the speaker again. And today's session comes to a close, and tomorrow we start at 10:30 Indian Standard Time. Thank you all. We'll see you tomorrow. Right. Read this log out first.